Thank you. Bye-bye.
I'm audible on Zoom. Can you see if I'm still audible?
Yes. Yes, I can hear you.
Oh, okay. Thank you, Professor John. Yeah, thanks. Hi, everyone. We will start in around 5 minutes to keep people some time, to give people some time to come back from lunch if they're still having lunch. So yeah.
Every now and then I'll see you publish like data moments.
Can we just get started in 2 minutes?
Sure. Yes, that's okay.
Let me know if you want to change at some point. You can change in the, break.
It's okay, yeah. I'll go out, come back, but my phone can't stay there. Onur wrote somewhere that he wants to make some remarks.
Where?
Not to you, or to
I know, not to me.
yes, I don't know. It's like a lot of Ghiasi. Yeah, the girl. And also like that's like to snow season. So when you do the introduction, it's like as compared to the remarks, it's snowing.
Okay.
No.
Hi, Sangwoo, how are you? Thank you. Very good that you could join. Thanks.
I'll be hiding them.
Thanks.
AI.
No, I could go and wash my body.
What's up? I'm still going to say hi. Across the state running for actually, I follow you on box and really, you're here.
I can write.
And I'm the same for the series stuff. The structure by myself. Okay. On my way out. I'm still no, yeah.
It took so long to say yes.
And Mohammed, you know Mohammed? Yeah. Who did not participate this year? No, he had to stay in Zurich because we also have the semester going on. There are a lot of lectures. Yeah. But now he's in the teaching over there. Okay. Unfortunately, what's up about new mitigation for Mohammed? Do you have any? Or you have stopped working there, Mohammed? No, we have seen working on that. I mean, some side effects. Yeah, it's really hot topic. After the discuss, and you have also worked, I think, in the same side effect on color channel and side channel. There is a section of paper, yes. So there were like two people.
Okay, Konstantina.
A boy and
I'm thinking of starting. Am I?
Yes.
Okay. Is live still also working?
And Ismail, the whole guy, he will present our team to focus on the search. Now we also have more house. Yeah, when you went to so he'll share some stuff about that. But it's clearly in the super connected session.
Okay, so maybe we can get it started now.
Why?
Sorry. Okay, hi everyone. Welcome to the first workshop on Architecture for Health, or Arch4Health. We're very happy you're here. So the reason we're having this workshop is that we have a lot of opportunities that have been enabled by recent biotechnological advances in generating high throughput, low cost, and accurate biological data in different modes and different aspects that can be used to enable unique opportunities in advancing healthcare. And these opportunities are precision medicine, bedside care, discovering early warning signs of communicable diseases, continuous physiological tracking, and more advanced diagnostics, and many more. But there are many challenges as well, and that is the fact that analyzing this large amounts of data on conventional system poses serious challenges that hinders enabling some of these opportunities in efficient and widespread manner. And these challenges include, but not limited to, performance and scalability issues, energy efficiency, privacy and security, cost effectiveness, and so on. So the reason we're having this workshop, and we hope to be having more of it and more discussions in this direction overall in our community, is to explore the key computational challenges in health-related applications and see what us as computer architects as a community can do to overcome these challenges and to contribute to advancing healthcare. And there are many example areas that deal with a large amount of data and many computational challenges. Some of them are in this slide, like computational biology, many aspects of it, neuroscience, wearable systems, sensors, robotics, medical robotics, mental health, medical imaging, agent-based simulation, and many more. So here also is a brief overview of us as organizers. This is me, I'm Nika, Mansouri, Ghiasi. I'm in the final year of my PhD in Safari Research Group, advised by Professor Mutlu at ETH Zurich. And we have here Konstantina. I will provide a brief introduction, but she will also give a presentation, so you'll get to meet her more as well. She's a postdoctoral researcher and lecturer in Safari Research Group at ETH Zurich. And we have also Professor Onur Mutlu, who is leading this research group as a professor of computer science at ETH, and is also here with us online. Onur, would you like to make some remarks? Do you hear me?
Yes, let me turn on my camera. Can you see me over there?
Let me see.
Okay. It's okay if not, but
Yeah, okay.
we can try.
Yes, I can see you.
Okay, hi, Lucy. Welcome. Okay, I think you can see now. I can see myself also on the screen. Okay, welcome everyone. It's great to have this workshop for the first time at Micro. This is an area that I've personally been interested in for many years. I started working on it since 2006 or so, especially starting with read mapping and genomics. And over time, I think there's a lot of interest in this topic. And the areas that Nika mentioned nicely are a limited subset of the areas that could potentially be looked at within the context of system design. So we wanted to start this workshop to gain more momentum and hopefully attract more researchers to this important area that's going to be growing into the future and that incorporates many aspects of computing, especially data analysis, but also a lot of decision making, prediction, So a lot of things we do in computing, computer architecture, computing systems design are actually applicable to health, and some of them can be in life-critical situations. So we're quite excited about starting the series, thanks to Nika and Konstantina's organizational efforts. I'll be there also in person later this afternoon due to some travel and scheduling mishaps. I couldn't make it right now, but I'll be there later in person. So I'd like to meet a lot of people as much as possible. And I should also say that there was a lot of interest in this particular incarnation of this workshop. It was difficult for us to fit everybody in schedule. That's why the talks are relatively short. So hopefully we can keep on time. But the next time we're organizing this is going to be at HPCA, and it's going to be a full day workshop. So we'll be able to accommodate the interest that came from the community. Thank you. See you soon.
Thanks, Onur. So now if I can, okay. 1 second, going back to my own slide. Okay, so here you see, oh, I need to go. Yeah, okay. So before we finish this introduction, I want to also show you here the agenda. Many thanks to our speakers who are here with us from different parts of the world and talking about many interesting directions from brain-computer interfaces, wearable systems, genomics, proteomics, metagenomics, and agent-based simulations. And yeah, you can see also a lot more information about these talks and about the workshop page here. And yeah, thanks again, and we will soon start with the first talk. Well, wait a second.
Oh, yeah.
So start with
Okay. So,
according to presentation mode.
okay, so should I show this one?
You can share your entire screen.
In our screen,
Yes.
like this?
Yes, let's see.
Okay.
And now press this.
Which one?
This one. This.
Slide. Okay.
Is it good for you?
Oh, yeah.
Super. And what?
So I do not need to connect to the HDMI.
So Nika?
Hmm?
Okay. Are you also sharing the screen now? You should stop.
I think this should.
This should be fine, right?
Yeah, maybe you can double click and make it screen.
If it was full screen, I need to
Oh.
just give me 1 second. I want to hide meeting control. Yes. Where is it?
It's usually
I guess we can go with this.
I think actually you need to do it. I'm sorry. You should maybe press here. Is there something here? High loading the need something like loading. Like
Okay, maybe.
yes. Great.
Yes.
I think.
Yeah.
I think good. And I'll just move this a bit to the side so that you can place his laptop.
Okay, perfect. So move it to the side so he can place his laptop. Okay, let's do it without anything breaking.
Whatever it reads.
Okay,
Okay, thank you.
You have to
can you give my mic? Because you can use this microphone as well.
so that you'll be audible on Zoom. Places. This there is a
Okay. Yeah, I can put it here.
yes. Right. Great. Okay. Just 1 second so that I can also introduce you. Just provide a brief introduction.
Okay.
So Hyunjun Lee is an assistant professor at the Computer Science Department at Hanyang University. His research interests lie in brain-computer interface, neuromorphic processor processing, in memory architecture, and approximate computing. Thank you so much.
Okay, thanks for the nice introduction. Hi, my name is Hyunjun Lee, and I'm currently working as an assistant professor at Hanyang University. And in this talk, I'll talk about our recent efforts over the last 3 years on designing a system for brain-computer interfaces. And this work was done with my colleagues over there, and thanks to them. And my research interests lie in these, and maybe the last one is one that may interest you. I'm working on the in vivo BCI signal processor. In other words, I'm working on a BCI signal processors for the living brain. And I presented 2 different papers last year and this year, and I'm also going to talk about our recent ongoing study. So about the in vivo BCI signal processor. So the BCIs directly records the signals from the brain, and when it is integrated with a digital processor, it can cure the neurological disorders such as seizure treatment or tremor suppression or visual prosthesis and on and on. So the figure represents the basic working pipeline. So first, the BCI records the signals from the brain and digitizes them to pass them to the digital processor. And the digital processor decodes the signals using, let's say, neural networks or statistics, machine learning, and on and on. And based on the decoding results, it stimulates a specific brain region. So that's how it goes. And there are multiple implementations of the brain-computer interfaces, or BCIs. First, there is a non-invasive BCI. So it simply places the electrodes on the scalp. It is simple, but it suffers from low signal resolution as most of the signals are observed in the skull and maybe scalp. So as an alternative, you can make a hole in your skull and directly place the electrodes in the brain tissue. This is also possible, but you need surgery, but you can benefit from higher signal resolution. And recently, there are some efforts to streamline this type of surgical procedures, such as Neuralink has developed a surgical robot that avoids the brain vessels when inserting the electrodes. And also, Synchron has developed an innovative surgical method which implants the electrodes through the brain vessels or blood vessels. So in this talk, we'll focus on the invasive BCIs. So the main challenge of the computer architects is that we need to design a processing system for this brain-computer interfacing thing. And there are generally 2 different approaches. One, we can rely on the on-BCI processing system, which directly utilizes the processing capabilities inside the BCI SoC. So this is nice. You can do an autonomous processing without any security or maybe reliability concerns. But the problem is that if the embedded processor consumes too much power, it'll overheat and damage the brain. For example, FDA has stated that you need to keep the power consumption down to around 50 milliwatts to prevent it from overheating. As an alternative, you can rely on an off-BCI processing system which wirelessly offloads the computation to an external device. For example, Synchron is using an Apple's Vision Pro, or Neuralink is trying to use a smartwatch or smartphone. These are all possible, but the problem is that it consumes too much power to wirelessly transfer the signals outside the skull. And also, the external system should operate for 24 hours, so it should also be energy efficient. To make the matter worse, again, as Nika stated, the BCIs are scaling up at a fast rate. So the figure illustrates the number of neurons that a single BCI node can record from 1960s to 2020. And as you can see, it's kind of similar to the Moore's law. It is scaling up at a fast rate. And the problem is that it incurs higher computation overhead and also high communication overhead. So these are the problems. So when we first started this project, we planned to design a single optimal BCI system by fully understanding the exact components inside the BCI SoC. And then we do a full-stack design space exploration to find the best system. So these were our goals. So let's look at the BCI SoC. So this is the figure adopted from Neuralink's N1 chip. And as you can see, there is indeed a signal processor inside the SoC. Neuralink has stated that it will implant a ARM core inside the SoC. But additionally, there is a BCI sensor. and there is a storage device, and there is also battery and radio. So we need to fully explore the design points considering the data collected from the sensors, and we also need to consider the storage, and we also need to consider the communication and power systems. And these were our research plans. So first, we designed an architecture considering the data collected from the sensor. So this was presented at Micro 2024. And then we moved on to design a system, a learning-enabled BCI system considering the storage embedded in the BCI SoC, which was presented in this year's ISCA. And we're currently working on a communication and power-aware BCI system by fully analyzing everything. And this is an ongoing study. And first things first, let's talk about the sensors. So the main challenge when we first designed the BCI processor was that your brain operates in a highly sparse and asynchronous manner using spiking information. However, when you're trying to process this type of spiking signals recording from the BCIs, it is highly efficient when you're using GPUs or MPUs because they are basically designed to support something dense and synchronous. So we thought that we need to close this type of semantic gap between how the brain operates and how the GPU and MPU operates. So the key insight is simple. So we thought, why not use the neuromorphic processors? So neuromorphic processor was primarily designed to facilitate the sparse and asynchronous processing paradigm of the brain. So we thought it would be a natural fit in the BCI context. So like representative examples could be True North or North Pole developed by IBM or Loihi developed by Intel. So we thought that neuromorphic processors can narrow the semantic gaps between how the brain operates and how the digital processors operate. But there was a problem. The existing neuromorphic processors are mostly optimized to support only neural networks, or especially the spiking ones, the SNNs. But there are various sparse and asynchronous processing kernels aside from the neural networks, such as spike sorting, pairwise correlation, and template matching. So these were not a natural fit for the neuromorphic processors. So what we did was to fully re-architect the neuromorphic processors for the purpose of flexibly and efficiently utilize them in the BCI context. And this was the solution. Pretty much simple. We pretty much redesigned everything, ranging from the compute unit. We designed a BCI purpose data path. And we also designed a custom synchronization unit for complex BCI workloads. And also we designed a multitasking controller, which was not supported in the existing or original neuromorphic processors. And also we designed a custom software stack. And the results were promising. Of course, this was published, so I will not dive into the details of the evaluation results. And let's move on to the second one. Second, we designed a learning-enabled NVM-assisted BCI system. So the main challenge is that in practical scenarios, the neural signals recorded from the BCIs continuously change over time. There are multiple problems. There is a neurogenesis, the neurons die over time, and also there is a neuroplasticity, the network structure changes over time. And even worse, when you first insert the electrodes in the brain tissue, there can be some sort of immune system which retracts the electrodes. So the probes drift over time. So the point is that we should maintain the high accuracy by adopting continual learning. So the figure represents two different decoding algorithms, one neural networks, another clustering, and the red line indicates the accuracy without learning, and the blue line indicates the accuracy with continual learning. And as you can see, you need a continual learning to maintain a sufficient quality. And another problem is that prior works start to integrate non-volatile memories into the BCI SoC to support large-scale and complex workloads. So again, the BCIs are scaling up at a fast rate, so the workloads scales are increasing, so you need to store a larger number of parameters. But when you utilize an SRAM, it consumes too much power, so they have shifted to utilize the NVMs. But you know the problems of the NVMs. They wear out, and it is really slow when you're doing write operations. So after adopting NVM and deploying learning-enabled workloads, you observe a sufficient, an extreme amount of overhead. For example, it suffers from 44 times higher latency, and also the complete storage may wear out within 5 months. So we designed InfiniMind, and when we were designing InfiniMind, we started out with the state-of-the-art BCI processor called Scalo, developed by Professor Abhishek Bhattacharjee, and we have modified the key processing pipelines, but more importantly, we modified the NVM controller. So first, we devised an update filtering mechanism which filters out redundant and small updates for continual learning, which can filter out around 95% of the parameter updates without sacrificing the accuracy. And also, we devised an LFU cache motivated by the fact that most of the parameter updates are centered around only a few set of parameters. And then we also developed a model compression, custom compression mechanism, which can compress the data for like 50% without sacrificing the accuracy. And also, it can sustain the sparse and irregular updates of the BCI workloads. And again, the results are promising, so I'll skip the evaluation part. And now, finally, let's talk about the battery and radio embedded in the BCI SoC. This is an ongoing study, and let's talk about the key motivation. So the main problem of the BCI system is that there are various BCI computing resources with trade-offs, different trade-offs in terms of the power budget and communication overhead. For example, you can utilize the BCI processors embedded in the BCI SoCs, or maybe you can rely on the smartwatch, smartphone, Vision Pro, or whatever. Or you may even rely on an external server or a laptop. And there is a clear trade-off between the power budget and communication efficiency. When you're using the processor embedded in your brain, it suffers from a tight power budget. Maybe using an embedded processors like smartwatch can relieve the power budget to some extent. Maybe using an external server, you have an abundant amount of power. However, when you're trying to use an external server, you need much powerful communication system to deliver the data over the longer distance. On the other hand, when you're using a BCI processor embedded in your brain, you do not suffer from the communication overhead. So this is a clear trade-off. So we need to consider how to manage these types of heterogeneous resources when you're trying to process a scaled-up BCI workloads. There is another challenge. So when you're designing a BCI SoC, there are diverse system configurations with different trade-offs in terms of data transfer efficiency and charging methodologies. So for example, when you're trying to transfer the data to an external device, you may rely on the radio frequency-based communication, RF-based one. For example, you may rely on the Bluetooth or Wi-Fi. This is nice in some cases when you're trying to transfer the signals over longer distance. However, it raises some safety concerns because the RF-based communication consumes too much power and it radiates energy, which may be observed in your brain and overheat the brain. Maybe there are some innovative communication method called body-coupled communication, and the key idea is that you can use your body as a communication medium. This is an extremely efficient one when you're trying to transfer the signals to a body-attached devices. However, you can only transfer the data to a limited distance. The destination should be attached to your body. Orthogonally, you may consider using signal compression, which achieves power efficiency at the cost of lower reliability. There is also a problem on the power system. Maybe you can rely on the wireless power transfer, which continuously transfer the power to charge the implanted devices. This is kind of stable, but you suffer from the radiation energy. Maybe you can rely on an energy harvesting systems by using a the temperature differences This is also possible, and it is biocompatible, but it is unstable. And there is also a trade-off in terms of the energy storage. Maybe you can rely on a primary or non-rechargeable battery. However, when you're trying to use a non-rechargeable battery for, let's say, 10 years, it'll weigh around like 1 kilogram or 2 kilogram. You cannot put a BCI implant with 1 kilogram battery. That is impossible. Maybe you can rely on the secondary battery like lithium ion. Cool, right? Because it may explode. As an alternative, you may rely on the energy supercapacitor, which stores the energy in the capacitor. This is also possible, and it may be designed in a biocompatible manner, but it suffers from low charging efficiency, and you can store only a small amount of power, so there is a lifetime issue. And lastly, the processor should support multiple applications, and also a single application may consist of heterogeneous pipelines. So, for example, the scientific analysis, there is no budget, but it suffers from high computation overhead. Maybe seizure prediction. It does not require much computation, but you suffer from tight latency budget. What about neuroprosthesis, medium budget, and medium computation? And within the neuroprosthesis, you undergo various kernels such as spike sorting, correlation analysis, and neural networks. So they are complex and heterogeneous application pipelines, which further complicate how you should manage these types of heterogeneous resources. So this is our insight. We need to design a full stack design space exploration ranging from the processing, communication, power, and we need to do a iterative bottleneck analysis to identify an optimal design point and come up with an optimal cross-level resource management policy. But this is an ongoing work, so I cannot tell you all the details. And this is it, and thank you for listening. So if you have any questions, just feel free to ask. Okay.
Oh, that's right. So could you elaborate on the instability of the energy harvesting method for the second challenge? Yes.
Oh yeah, because there is indeed an instability in the energy harvesting because you cannot guarantee a stable power source. In some cases, your body may overheat and the energy harvesting may work properly, but in another case, when you're cool, you cannot harvest too much energy.
Can we trigger some inflammation, for example, to increase the body temperature and harvest energy from there?
Oh yeah, I think that could be possible. You can heat yourself and make yourself overheat. Yeah, that could be possible.
I understand what you mean.
Oh
Thank you
yeah,
very much.
yeah.
Other questions in the room? Yeah, wait. I can also give you a mic. Maybe you can be more audible.
I wanted to ask more general, when you work in this field, do you work together with hospitals, or how do you conduct your research?
Actually, when I first started this project, I did not have any collaborators, so I had to work on my own, but there are like abundant resources, open source resources on the data set of the neural signals, maybe from monkeys, or there are some limited amount of human data. And after doing this kind of project for 3 years, I do have some hospital collaborators. He's implanting the device on the monkey. Yeah, so I get the data from there.
Thank you. It was really interesting.
Okay.
Maybe I can also build up on that question. I'm curious. So based on the real data that you're collecting compared to some benchmark data that you had before, are there new insights or new directions that you see differences? Like what did you learn from real data and how can it propagate?
Oh, actually, yeah, I'm just starting to see the real data, so I do not have much information, but one of the main benefits is that maybe most of the data are related to the hand movement. The open source data sets are related to the hand movement, but I'm currently getting the data for the leg movement, which is kind of different. So, yeah.
But still very interesting that you can access real data.
Okay.
Great.
So you just mentioned that the data is on the monkey's side, right? Like when you translate that to humans, how much of a difference you would see?
Actually, I cannot expect that because most of the human data are related to the seizure related data, but the monkey data are more like related to the movement intent. So it's like whole different data sets, so I cannot directly compare those two, but
So in that case, these results or like the procedures that you were thinking of, would you have to change them when you shift the data sets?
oh yeah, I really need to think about it, but I haven't really thought about it.
Sure.
So,
Yeah.
yeah.
Thank you.
Maybe that's a topic we can hear more in the next iteration of this workshop as well.
Okay. I'll definitely go to
Very
BCA.
interested to hear. Thank you so much for your talk. That was very interesting. Now the next talk is on.
Yes, it's online, the next one.
Would you mind?
So
Mic is.
it's on. So
Can I
Professor
share?
John, yes, maybe you can share your screen.
I took the one.
Yeah, it's okay. Thank you. Thomas.
Probably.
Okay, so we can see your screen.
Okay, and you can hear me too, right? Audio is okay. Is the audio okay?
Yes, I can hear you.
Yes, we also hear you in the room.
Oh, okay. So can I just start?
Yes, please. Oh, no, sorry. I wanted to provide the speaker bio. Sorry. Still gaining experience in this. Okay. Professor Lizzie John holds the Turchard Foundation Chair in Engineering in the Chandra Family Department of Electrical and Computer Engineering at the University of Texas at Austin. She received her PhD in computer science from the Pennsylvania State University in 1993. She joined the University of Texas Austin as a faculty in 1996. Her research is in the areas of computer architecture, multi-core processors, memory systems, performance evaluation and benchmarking, workload characterization, and reconfigurable computing. Yeah. Thank you.
Hi, good afternoon. So I will talk about energy efficient neural networks for medical wearables. So these are wearable neural networks. And so wearables matter a lot in health. Continuous monitoring versus clinical monitoring, like if you can only measure your blood pressure when you go to the doctor or a clinic, versus if it can be continuously monitored. It helps early disease detection, it helps to manage chronic conditions. And if personalized solutions, in wearables, that way it helps basically like not one solution for all, but possibly personalized solutions. And continuous monitoring is also very helpful for post-surgical management of patients. When patients are discharged after surgery and they go home, continuous management can be helpful, and wearables are good for that. So, and the wearables have been evolving over the past multiple decades. Whether they are miniaturized systems in clothing or skin patches. In the 2000s, mostly there were step counters. In the 2010s, smartwatches started appearing. 2020s, there are ECG, blood pressure, glucose monitors that can be used, sensors for doing those. And on-device AI for diagnostics is becoming common. So there are various types of wearables and various types of sensors and multiple signals from the body that can be measured. And in the sensors, the physiological ones are ECG, PPG, temperature, oxygen, and motion-wise accelerometers and gyroscopes help to sense motion. And there are also sensors for sweat glucose, cortisol, etc. All of these can help. And now coming to the computing in the wearable. So on the smaller end, denoising signals, but then detecting anomalies, or sometimes it's we are used to having activity trackers or sleep trackers, but the classification and there is processing involved there, and predictive analytics for early detection of the disease coming or disease onset. But wearables have very tight computing requirements, very low energy consumption, otherwise the battery will drain. They shouldn't be producing heat, otherwise the thermals, then you cannot wear it for too long. They should be compact, and if there are wires attached to these, then it becomes very uncomfortable and it's not that suitable for, except when you are sick, like you have lots of wires going to the central monitoring place. So wirelessly connectable, wireless connection is great from the point of view of no tethering. We don't want very expensive devices. It should be low cost, so it's accessible for the general population. And we want them to be accurate, that there are not too many false alarms, and it doesn't lead to, it's useful and not very overwhelming for people and healthcare providers. So AI has made an impact in every field, and of course in wearables too. And in order to make them energy efficient, most neural networks, can be quantized, they can be pruned, so they become smaller. And quantization helps. Even binary neural networks are there. There are event-driven AI is another approach, and you only act with certain events. So there is, wake up with certain conditions. Duty cycling, so you don't have to, if there is no problem, maybe you don't have to monitor the whole time, and some duty ratio can be used to cycle it and monitor it periodically to save power and energy. But energy efficient AI models are needed in order to do, to be useful and or to create good wearables. DNNs are not a match for wearables. DNNs have too many weights and too many multiplications and addition, too much of computation, and hence too much energy consumption. So they are not suitable for wearables in spite of quantization, pruning, and compression techniques. So I'm going to talk about something called weightless neural networks as a wearable neural network, low energy, and many other attractive features as well on the privacy side, explainability side, etc. These are based on, this is RAM neuron, which is a 1959 paper, and basically memory structures. So here 4 memory cells are shown, 2 bit inputs or addresses. And so this was at that time proposed as a pattern recognition machine. And weightless neural networks, this have a little bit more similarity to dendritic computing and dendritic decoding that happens in the brain. It can be created by these memory-based or RAM neurons. Also, in another way, looking at the RAM neurons, a RAM structure or a lookup table is very expressive. So a lookup table with 2 input variables, that's 4 locations, can actually express any one of 16 logic functions. So for the 2 input functions, the A and B are the inputs here, and the 16 functions are listed here. There are 16 functions, or 2 to the 2 to the n functions, because in this case, there are 4 combinations of outputs, and they can be all zeros to all ones and 16 combinations. But this, as n grows, this grows very heavily. So basically, if you have a 6 input lookup table, which is common in modern FPGAs, 2 to the 2 to the 6 is a huge number. 2 to the 6 is 64, so 2 to the 64 is a very big number. So if we can learn which among these functions is what you want to be intelligent in that scenario for that neuron, if it can be learned, these lookup tables are really powerful structures. So you can build a neural network with lookup tables, and they are very expressive. And we need to be able to learn which among these functions do you want. So there was a classifier built called Wizard in 1984. This was from the Imperial College, so in UK. So there are these ramps. These ramps, in this case, if there are 3 inputs, so it is, with 3 8-bit locations. Input, the pattern or the input you are recognizing, that is randomized in this case. That's what Wizard did, and fed to these RAM neurons. And then, so this whole thing is called a discriminator. For every class, this is a classifier. So if there are 10 classes, each class needs a discriminator. And when a new input for the inference is presented, whichever discriminator has the highest response, that is the inference. And the training, and this Wizard stood for the names of the people who built it, Wilkie, Stoneham, and Alexander. And the training mechanism is a one-shot training in Wizard. So you basically present an input, and the RAMs are all corresponding to the mapping. The RAMs, whichever location has something an input, so they become 1, and the other locations are 0. So the ones go to certain locations. And then, so that's what, and every training data is presented once, and the locations change accordingly. Now, during the inference phase, a new input is presented and the same mapping, and things go, and then you sum up for each discriminator, you sum up all the ones, and whichever discriminator has the highest response, that's basically the class we are inferring. And these lookup table based networks, there is a metric called the VC dimension that tells for a binary classifier, what is the amount of the complexity of the knowledge it can represent. And the VC dimension for a weightless neural network is very high. For a DNN neuron, it's n plus 1 for n inputs, and for a lookup table neuron, it's 2 to the n. So even in a small example, like an exclusive OR function, a DNN would need 3 neurons and 9 parameters. The weightless neural network will only need 1 neuron and 4 parameters. Lookup table neurons are nonlinear, and biological neurons are nonlinear too. And this is a paper from neuroscience about the nonlinearity of the biological neurons. So we have been working on this for about 4 years now. This is a 2022 PACT paper. The red line is the baseline DNN models. In this case, they were MLP models. And these are all the corresponding weightless neural network models. So you can see they consume less energy, less dynamic as well as static. And these are ISO accuracy. For the same accuracy, so it's not the biggest DNN model or the most accurate, whatever is equal to their ISO accuracy models. So during the past 3 years, we have made progress in improving the accuracy of the weightless neural networks, and all without increasing the size. While actually here the red line is showing the size, so the size is reducing as well. Now, more recently, the most recent one is called the differentiable weightless neural networks, and that was a 2024 ICML paper. In general, the challenge in lookup table-based networks is lookup tables are not differentiable, so training is difficult. and the usual gradient descent doesn't work. Original weightless neural networks were single shot learning, but in order to improve the accuracy, we did have multi-shot learning, and then you need gradients don't work. So we needed to come up with a technique, and that is in the differentiable weightless neural networks. So here, this is an approximate gradient that is found using what is called extended finite difference technique. And we also, in this one, we have multiple layers of lookup tables. And so this has improved the accuracy significantly and reduced the size also of weightless neural networks. So, and we evaluated DW1s on 4 different scenarios. These are presented in the ICML paper. And FPGAs are very suitable to implement this because they have lookup tables inherently. But for many of the wearable applications, many wearables use microcontrollers. So a microcontroller implementation is useful. Although microcontroller implementation, there are several challenges because we are dealing with bits, and good bit packing need to be done. Good efficient optimizations, efficient bit packing need to be done in order to make the microcontroller models work well. ASICs, we can make with a very tiny gate budgets, we can make tiny ASICs. And this is also very good for tabular data. That's where one place the weightless neural networks are looking very good. So this is for keyword spotting. And in the case of keyword spotting, so we are comparing with very tiny neural networks. So the fin is from Xilinx, binary neural network, and a framework to train them. And they get on this keyword spotting data set 70.6% accuracy. And this is our earlier weightless neural network, Ulene, and DW1 is the newest one in the ICML paper. So we have good accuracy with significantly smaller parameter size, significantly smaller latency, so high throughput, very low energy, and very low hardware requirement. So the DW1 has significantly reduced the amount of hardware you need in order to get good accuracy. So we are claiming it to be nano ml, nanosecond latency, nanojoules per sample energy. So it's basically nano ml. And for a human activity recognition data set, and these are all the previous works with the accuracy, and we are able to be comparable in accuracy and F1 scores with tiny networks, 19 kilobytes or 39 kilobytes as opposed to megabytes here. And similarly, in the energy, it's nanojoules as opposed to millijoules. Now, there are more data in the DW1 paper in the ICML. I'll just go and show some very low cost, tiny networks. This one is, this was a paper in Nature in 2024, tiny classifier. So the tiny classifier, which is in the last column in here, they have with 300 NAND gates, they make the best classifier for these data sets. And this is the accuracy they have. Now we could, DW1, the first 2 columns, is beating the tiny classifier from the Nature paper. Both in capacity, gate counts are small, much smaller than 300 in many cases, and accuracy is better. So in general, 5x smaller area and 8% better accuracy. Now, what have we done in the medical field in order to do this? So continuous cardiac stroke volume monitoring. This is research in collaboration with Professor Nanshu Lu in our mechanical engineering department. So it's a continuous health monitoring platform and so she has been working on something called the e-tattoo. So the e-tattoo sends the signal Currently, what they do is on the e-tattoo, there is also a microcontroller, a very tiny ARM microcontroller. The microcontroller will send the signal to a phone or a computer in order to be processed. There is no processing on the microcontroller because you cannot fit in ordinary neural networks there or ordinary AI processing. So it looks like this. So these are the components in the e-tattoo. And the e-tattoo, currently, there is no embedded processing right there. It just gets the signals and transmits to the processing place. But we are able to fit in these weightless neural networks on this and human testing. There's actually a graduate student in the lab, and this is the weightless neural network that is used. And we basically can be measuring, and this is the golden value with the medical grade stroke volume machine. And then this is the weightless neural network, and reasonable accuracy and very low energy, and on processing on the tattoo itself rather than processing away. The same thing can be done for blood pressure monitoring, and we are working on it. And also, since in the interest of time, I will talk about one more thing we have done: arrhythmia detecting chip on a plastic substrate. This was done with Pragmatic, which is a company in Cambridge, UK. And so they have a technology which is basically a plastic substrate. On the plastic substrate, it is so it's basically bendable, flexible, and very nice for wearables, definitely. However, the capacity of the gates they can fit is 10,000 gates. So, and it is a 600 nanometer technology. Ordinary neural networks do not fit on it. However, we were able to train a neural network for detecting arrhythmia in about 3,000 gates, and we were able to fit it. And a chip was made, and this is the photomicrograph of the chip, and it was tested and found to be working, basically. And this was published in the International Flexible Electronics Conference in 2024. And so we are very excited about things that can be done with weightless neural networks. Now, in general, when you think about wearables and sensor reliability needs to be good. Many of these sensors are evolving. Battery life needs to be high. There, weightless neural networks can help. Algorithmic transparency. The one-shot training based weightless neural networks, they are completely explainable. They basically, the privacy can be guaranteed. Unlearning can be done if some other data was used and you have to remove it, you could remove it. So you could actually have many advantages from the learning point of view. But we need to build user trust and ethical issues. All of those are general challenges, and weightless neural networks have some advantages when you use them in the wearable field. So weightless neural networks are indeed wearable. Computer architects should architect light, energy efficient computing and AI for medical applications, so medicine 3.0 can become a reality. I would say for architects, future looks bright. I think wearables in maybe 5 years from now, maybe giving a lot of diagnostics right on your wrist. That's quite possible, much more than what the Apple Watch does now. Apple Watch can detect one type of arrhythmia, but it cannot detect all the different classes. And it's very expensive as well. And our objective is to make it cheap, that it can be more accessible to people. We have an upcoming article in IEEE Computer Magazine in January 26 in a technology prediction issue. And it is basically, it has some content similar to what I talked. And thank you for listening. More details on the ICML paper you can get from, you can scan this and get it, or look in the ICML proceedings. Thanks to my wonderful students who are working on it, and also the National Science Foundation grants. And on the second grant, it is also in collaboration with Intel, Micron, Samsung, and Ericsson. So I am grateful for all the funding. And questions?
Thank you very much, Professor John. Do you hear us in the room?
Yes, yes, I can hear.
Okay, perfect. Yeah. Thanks, given that also it's 2 a.m. in your time zone. Yeah, highly appreciate that you could join. So questions in the room?
Maybe
Yes,
I can
maybe.
ask.
Yes.
Yeah, okay. Can you all hear me? Okay, so you have described a lot of different applications and the use of neural networks. A question that comes to mind is how easy it is to attain the data sets to do the training, and if there are like privacy concerns and issues that become a bottleneck to creating more impactful such neural networks.
Yeah. In this work, this is a publicly available data set that was used, the MIT BIH data set. We would actually like better data or newer data. However, this was the most common data set that's available that was used here. But for this one and this one, the data is actually generated just in their lab. So we have very limited data. Because Professor Nanshulu's group, they do these types of research, and e-tattoos are developed there, and they are using e-tattoos for many applications, mental workload prediction. They have sweat sensors, nervousness, anxiety, and a whole bunch of things. So they collect the data. So they have human subjects participating in the experiment, and mostly students from the university. And so they collect the data, but still it is very limited. It's not like thousands of cases. They have tens of students participating. Each student goes through the test for maybe 30 minutes, which gives a lot of data points. And they change the position, so they make variability in the data by doing the experiment in different positions, etc. There are no public data sets for this e-tattoo and the blood pressure and the stroke volume with this. So if we were to use some other sensor and a different mechanism, maybe there are some public data sets, but in this case, data generation is definitely a problem. The good thing about weightless neural networks is it does well with low amounts of data. It doesn't need as much data as what the DNNs need. So we have been able to apply them in this case.
Okay, thank you very much. Thank you for your answer. So Nika, back to you.
Yes. Your questions? Okay, then thank you so much, Professor John, and have a good
Thank
night.
you. Thank you.
So now the next presenter. Yeah.
Oh, push spotlight again.
Yes.
Okay, so we're gonna use hopefully.
Yes, many wires make it difficult.
Exactly. Using the mind of brain surgery, like moving all this.
Well, we lost the connection to the projector.
Oh, yeah, there was a picture. Just okay.
We don't care.
Yes. Done. Maybe I try to make it. I try to open the slides.
Maybe unplug and plug again.
Nothing happened. Why is this happening? The projector is not good. But it is, could it be something that happened by that?
Do we need to hit this?
No,
Okay.
it doesn't sound. Great. Okay, great. Okay, so just I share the screen also on Zoom. Oh. That's the wrong window. That's okay. This should be, doesn't have to be there.
I think it disappears if you
Yeah, you don't have.
unfocus.
No, I want to share the screen, that's why. You don't need to post it in person, and on YouTube it's already embedded. So no, I have not shared the screen, that's the point. Okay, that's the screen. And I share. No, it's not okay.
Yeah.
You feel okay, and now just change the mix. This is your pointer.
Thank you.
And then you should wear the microphone. Nika, do you have
I just provide a brief bio and then we get going.
you can wear it.
Thank you. Hello?
This is not for volume, this is for the Zoom. Yeah. For the volume,
Sorry.
for
I was harassing people on Zoom just now. Okay.
All right, so we have multimodal presentation, experience context, which takes time. But yeah, so Sang-Woo Jun is currently an assistant professor in the computer science department at the University of California, Irvine. He earned his PhD in electrical engineering and computer science at the Massachusetts Institute of Technology in 2018. And he earned his bachelor's degree in electrical and computer engineering at Seoul National University in 2010. His current research interests are innovative system architectures for low-cost, high-performance computing. Professor Sang-Woo Jun's two prominent tools right now are non-volatile memory and reconfigurable hardware accelerators. Thank you so much.
That's not the bio I sent you over email. I'm just kidding. That's fine. I just noticed. I'll pretend to be. Thank you so much for the very nice introduction. It's a great honor to be here presenting some of our recent work in architectures for health. Yes, very nice to meet you all. My talk will be a little bit more narrower in focus compared to the very grand and overarching talks we've been seeing so far. So hopefully this is also a little bit interesting. So because we do a lot, I mean, I'm part of the ARDA group at UCI. ARDA, if you are a Tolkien fan, it's the universe. So that's kind of cool, but it's actually short for architectures for data. So we do a lot of architectures in the context of data. Genomics happens to be one of the things that we're really excited about right now. And it wasn't always like that. It was a very funny and winding rabbit hole we fell into, because at one of the conferences that I attended, one of the architecture conferences, I had a chance to talk to a biologist at an architecture conference, like a proper biologist, knew nothing about computers, well, a little bit about computers. He knew how to type in commands into Linux. And he told me something very interesting. He told me, we have been running a single next-to-novo instance for 1 year in a 1 terabyte AWS instance. We don't know how long it will take. I hope it finishes soon. And I was elated. Hooray, an architecture problem. Maybe at the moment I was thinking it's probably not an architecture problem. This is a biologist who knows evidently nothing about computers. This person does not know, the order of the slides team, I'm sorry. What he was trying to do is, as the tool name suggests, but a lot of us are not familiar with the tool, he was trying to do what is called de novo sequence assembly. So as a very, very shallow background, when we do genomics, we read samples from sequencing machines, right? And because these sequencing machines still cannot just read a genome from beginning to end in a single string, they give us kind of the shotgun sample of random locations in bits of the genome. And there's a few different ways that people assemble this back into a single string, or at least 23 strings for humans. One of them is reference-based assembly, because thanks to the Human Genome Project and a lot of things that came after that, we do have a bunch of pre-assembled reference genomes for human beings. And because humans share like 99 point something percent of the same genomic data, we can assume something that looks similar to a location in the pre-assembled reference is going to actually go to that location. So there's a thing called reference-based assembly, which is reasonable. The other thing that's done sometimes is what is called de novo assembly. De novo assembly is if you don't have a pre-assembled reference or for whatever reason you don't want to use a pre-assembled reference. The consensus seems to be that a lot of data scientific errors that can come from pre-assembled references can be kind of sidestepped if you do a de novo assembly work. Stuff like things that I don't honestly understand very well, things like reference drift apparently happens in reference-based assembly. So if you want really, really high accuracy, a lot of people would like to do reference-free de novo assembly. There's a bunch of very good characteristics that come from that. Of course, nothing good comes for free, so reference-based assembly is kind of cheap. Right now, if you want to do it on a desktop class machine, apparently you only need something like 32 gigabytes of memory. It takes a few hours. It's nice. If you do de novo assembly, then you run a 1 terabyte AWS instance for 1 year. Of course, the problem for him, the collaborator who eventually turned into our collaborator, was that he wasn't even working on a human genome. He was doing crop agriculture research. So he doesn't have a reference genome in the first place. So he has to suffer that 1 terabyte AWS instance, and it was eating up a lot of his funding. So I was elated because, this is someone who, obviously there's a problem. And a real financial problem. And I was thinking, this guy doesn't know about GPUs, was my first thought. Because, NVIDIA would tell us, which is, very, very true and very, very cool, that they have been increasing their GPU performance at a rate exceeding Moore's law for some time. And lo and behold, they also do have at least a big portion of the tool that these guys were using accelerated with GPUs. And I thought this would be a very interesting and fruitful collaboration, which was going to last maybe a few weeks. That was my thought at the time. This is going to be easy. What we discovered was, first of all, the Minimap, that thing should have been animated, I'm sorry. Minimap 2, as implemented inside Parabricks, the NVIDIA provided package, does not support this one feature that we actually need to do this work. So that was a bummer. But even kind of ignoring that, performance looked kind of funny. So we tested the performance of the GPU accelerated thing versus a fully CPU implemented original implementation using a fairly decent set of hardware. The Xeon Gold processors, we had like 48 cores, and an NVIDIA A100, which is already starting to get a little bit outdated, but it was really nice at the time. And the performance that we saw was this. Lower is better because x-axis is time in minutes. And you'll see that the A100 GPU, which cost us a lot of money, was worth about 16 Xeon Gold threads, which is absolutely not what we expected. It's not, it was sad. So it didn't turn out to be as easy a problem as I thought it was. So the question, we started digging into what was going on here. So that begins the story of our rabbit hole. And so this is a chart that we found from a paper which, at least one of the papers that the Parabricks implementation is based on. And we discovered that of all the things, heavy lifting stuff that goes on inside the tool, only 2 of the actual components, high computational overhead as they may be, are only implemented inside GPUs. And why not? What about all the other things that also have a very high computational load? And the thing turned out that a lot of these things actually are not a very good fit with GPUs. If I take one of the components, which is Smith-Waterman algorithm for alignment, which is a very big part of the computational overhead of this algorithm, it consists of 2 steps. The forward path, which fills up the distance matrix, and the backwards path, which reconstructs the shortest path that it took to get to the shortest number. And it turns out that the forward path is very, very easy to parallelize because it's basically a parallel wavefront algorithm. There's a lot of parallelism. It's very, very memory intensive. It's really, really good for GPUs. The problem was in the backward path, it's basically it's basically like trying to parallelize a Dijkstra's algorithm. It's very irregular, it's very sequential, it's very branch heavy, very, 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 very bad for GPUs. CPUs are just much, much better, at least at this step. So a lot of the tools what they end up doing is accelerate the forward path inside the GPU and then just ship the matrix back to the CPU to do the backtracking path we discovered. The additional problem was that when the matrix construction work, the forward path was being offloaded to the GPU, the two sequence information, the L and S sequences, which are being sent to the GPU, is only, let's say, of length n, so 2n. But the constructed matrix now was size of n squared. So that was just completely just choking up the PCIe. So the tool was stuck very, very deeply between a rock and a hard place. Do we suffer the performance overhead of doing backtracking on the GPU? Or do we suffer the performance overhead of sending a lot of data back over the PCIe? So that was kind of core of the problem. So that's been the rabbit hole we've been stuck in for a few years now. So we actually have a few interesting ideas that I think we will solve this problem, but that one's still kind of not done yet. So I'm going to, and on the path to discovering all these problems, we discovered a lot of similarly data movement bottleneck problems. And here's another one. Again, we were trying to see if this tool doesn't work for us, maybe we'll use a different tool. For example, there was apparently this, unlike Minimap2, there's this other tool called LastZ, which has a slightly different target, but it is also a genome mapping tool. And this one was very interesting because the runtime breakdown of the tool's execution was very, very skewed. It might be a little bit difficult to see because it's in kind of light green, but something like 97 to 99% of the runtime is dominated by what is called the filter phase. I won't go into too much details about what this is, but it's very obvious that we have to accelerate that. Good news is, I mean, Nika's very, very, very familiar with all of this, but, sorry. I should think that. The good thing is there are a lot of people, this is an important application. A lot of people have done research into building FPGA/GPU implementations of filtering or pre-alignment filtering and all these algorithms. So there's a very good set of algorithms out there which work really, really well, low overhead, or they have a really, really nice FPGA or GPU implementation. The problem again is we are again bottlenecked by PCIe. A lot of these implementations have very, very high internal throughput, we discovered. Things like Sneaky Snake or Seedhead. These have very, very efficient GPU implementations. Unfortunately, because their operational intensity is very, very low, data movement over PCIe just bottlenecks everything. Because the data has to come from somewhere. It has to be generated by the sequencing tools. It has to go to the accelerators first, but that just completely kills the performance. So in the world of roofline analysis, we were stuck somewhere here. You're seeing this face a lot because there's a lot of problems that we have to solve, which is really, really great. So in this kind of a situation where data absolutely has to move somewhere, but bandwidth limitations bottleneck everything, the go-to solutions that we had in our research group always was to try some form of compression. Because if you can compress data by 10x, we improve the efficient bandwidth of the PCIe by 10x, and that will maybe help us. Yeah, and we've done this a lot. We've done this with a lot of different applications, a lot of different data types, floating point, random numbers, text, a lot of these things. And we were kind of confident if we tried to do this on this data set, it'll work as well. Unfortunately, compression doesn't really work well with genomic data. We tried a lot of things. It was quite shocking to discover. All compression algorithms, I should say data agnostic compression algorithms, get almost no compression on genomic data. The entropy appears to be just way too high. And we felt like someone was playing a practical joke on us because anything we try, we come up with a new idea, we increase the dictionary size, we do this, we do that, we sort the data. And if we manage to shave off a little bit of the encoding, the dictionary size expands almost to the exact same level so the compression becomes exactly the same amount. It felt like some deity was playing a trick on us. Deflate all the LZ series, like even genome-specific algorithms like DNA bit, they give us, like, if we start with an 8-bit ASCII encoding, it gets us to 2 bits per character, which is basically 2-bit encoding ACGT, and nothing more. It was, it felt like we were against some law of the universe. It was very, very fun, but also very, very frustrating. What ended up saving us was there's another algorithm called, a class of algorithm called consensus-based genome compression. And again, because a lot of this individuals in the same family of organisms share most of the genome data. So if we have a reference, so-called a consensus sequence, and we're trying to compress an original genome sequence, and if we can discover long matches, we can instead encode the locations of the matches and the length of the matches, and that works really, really well in terms of compression efficiency. The good thing about this is these class of algorithms give us really, really high compression efficiency, provided that we kind of ignore the capacity of the consensus sequence. But that's maybe okay because we only need one for every single family of organisms. They give us really, really high compression efficiency, 10x to some algorithms even achieve 1000x on some publications. The problem is they're very, very slow. Even GPU implementations max out somewhere around 1 gigabytes per second. So this works really, really well for archiving purposes or data distribution purposes. But for our purposes, which is to kind of improve the effective bandwidth of the PCIe, the algorithm itself was becoming a bottleneck and not being very useful. After some more digging, the problem seemed to be because the algorithm was trying to support variable length matches. During compression, because we wanted to support variable length matching, they were using something like a suffix tree. For every single character that needs to be encoded, it had to go through multiple steps of querying the suffix tree, which was, you can imagine, very difficult and memory intensive. For decompression, especially if we're trying to implement this in hardware, because these matches, they have to be processed at very wide widths to support high bandwidth. And because the lengths were variable length, we had to do a lot of shifting to compact the matches into a contiguous sequence once again. And that was killing performance. It was taking up a lot of chip space, a lot of bad things. Yes. And because of this, high compression ratio wasn't translating to high PCI effective bandwidth. So after a lot of banging our heads against the wall, the solution we started testing was trying to do a hardware algorithm co-design to change the algorithm so that it kind of facilitates a more easier hardware implementation. This is going to be presented at PAX in a few months. And the thing we tried to do was removing variable length anything. We tried removing variable length matches. The matches are going to be an always fixed length, K. Hopefully we can find a good K. And now, because the matches are not going to be variable length, matches can now be discovered with a single hash table lookup, actually 2 hash tables lookups because we're trying to use cuckoo hashes, but O of 1 hash table lookups. And in the case of mismatches, we also remove variable length mismatches. Mismatches are always fixed length stride, 1 stride, 2 stride, 3 stride, whatever. It has to be units of stride. Hopefully they're a large stride, and also hopefully we can find a good stride value. And now compaction requires only fixed width shifts, which is very, very efficient to implement inside hardware. Of course, this is all very nice. Oh yeah, this is the person who spearheaded it. He now is just recently became an assistant professor at Kookmin University here in Korea. Very excited. He's going to keep working on this, I hope. But of course, the question becomes, will these restrictions obviously translate to good and efficient hardware? Will these restrictions also will these things harm compression? The short answer is, of course, yes. And we tried to overcome this a little bit with some things put in to reclaim some of this compression. So by default, K, the value of the match, needs to be quite large for compression to be useful. because when there are matches, the matches must be encoded as an offset. And for human genome, this is going to be at least 32 bits. So if, for example, if K is only 16, we won't get any compression as a result of any of this because, 16 bases with a 2-bit encoding turns into 32 bits. So if we're trying to encode 32 bits with a 32-bit encoding, which doesn't make any sense. If K is 128, assuming all K-mers are matches, we get 8x compression. But we discover that if Ks are too large, then the probability of getting matches decrease. So we're going to get a lot of mismatches. So we don't actually get to 8x. So the solution we came up with to kind of reclaim some of the bandwidth is to add another type of match called the continuation match. If we have two subsequent or more, hopefully, subsequent contiguous matches, and they happen in the right, contiguous location in the reference, then we just mark that as a continuation inside the header. We don't actually encode the offset, but basically, hopefully turning it into variable length matches, something similar to variable length matches again. Yes, there's no payload in this case. And based on that, we tried to also get as efficient a hardware implementation as possible. First of all, because K can also be kind of small, and I'll show later that the actual K value we settled down on is actually 128 bits, which is quite small to get high compression efficiency. But the memory interface of, let's say, DDR4 or HBM is typically something like 512 bits. So if we just have a sequential, random access into 128-bit K, then we will have 4x IO amplification, which would again kind of kill performance. So we built some interesting little modules which coalesces consecutive lookups if addresses are also consecutive. And at the same time, because the memory access has latency, a significant amount of latency, at least 200 cycles at least in FPGAs. So if we do this in a sequential way, if we have to wait until we decode the previous value, if we have to wait until we finish decoding the previous value to start decoding the next one, we will be latency bound into memory, and that will kill performance. So we came up with the scheme where we group headers up to actually 16, sorry. 16 lookups are grouped together in a group header so they can be determined in parallel. So all of these little tricks we tried to come up with to achieve both compression efficiency and efficient hardware implementation. Yes, so the answer to the question. So all of these hardware efficient optimization, did they impact compression? Yes, they did compared to a more thorough default search, but with a well-chosen K and stride values. So for example, x-axis here is the stride value, x-axis here is the K value, y-axis is the compression efficiency. Apparently, stride value doesn't really impact compression efficiency on various types of organisms. K value does impact it sometimes, so maybe 64 is a kind of a good number. 64K would translate to 128 bits, 2-bit encoding. But with these well-chosen values, we were getting pretty competitive compression efficiency. So that's us getting above 10x compression efficiency, even with all of these things put in place. These other algorithms are genome-specific algorithms. At least this one is a reference-based compression algorithm. Some of these others are non-reference-based algorithms with a bunch of tricks put in to decrease they change the ordering a little bit to decrease, but that's not important. So with over 10x compression, our 16 gigabyte PCIe does turn into 160 gigabytes of effective bandwidth, which we were very excited about. Yeah. So ideally, it would turn into 160 gigabytes per second. So we implemented a prototype for this using FPGAs, as one would, using the Xilinx Alveo U50 FPGA platform, a mid-range ultra-scale plus card with an HBM. And we populated it with multiple parallel decompressors and compressors. Each decompressor needs at least access to its own 768 megabytes of HBM to store the entirety of the 2-bit encoding human genome. And each compressor needs access to its own 2 gigabyte of HBM to store the cuckoo hash. But I'm not going to talk about that here because I've been told I have 15 minutes of time. So we're going to focus more on a little bit on at least the decompressor. And even with the for the decompressor, we were very happy with the results that we got. We were getting 10x compression, and the implementation of the decompressor was turned out to be very, very efficient. We were getting really nice performance. So this is us. And we were getting roughly 16 gigabytes per second, near 16 gigabytes per second of decompression performance per pipeline. And each pipeline consumed only something like 3% of the U50 FPGA, which was U50 itself isn't a very big FPGA, but we were very excited with the results. So very small amount of LUTs, very high decompression efficiency per pipeline. So compare our 16 gigabytes per second decompression performance against a more vanilla compression algorithm implementation, where, for example, that one paper was evaluated with one whole V100 GPU, and we were 4 times faster with 3% chip space of the FPGA. And compared to a whole one Stratix 5 FPGA, we're getting really, really nice results, thanks to the co-optimization of the algorithm. Yes, and in context of the actual algorithms, sorry. Oh, sorry. With 5 decompressors, we are already reaching DDR4 levels of bandwidth and 34% of the raw HBM performance. The reason I'm talking about power throttling here, because on the U50, the HBM we discovered is power throttled at something like 7 watts. So it doesn't actually give us 512 gigabytes per second. It was promised to us. So this is the actual numbers we measured. If we assume we use a actual, non-power throttled HBM, which actually will give us 512 gigabytes of advertised bandwidth, we will probably get 2x of DDR4 bandwidth over the PC while thrashing PCIe, and again 30-ish% of peak HBM performance, which was really, really nice. And even at 2x of DDR4 performance, thanks to the really, really high compression efficiency, we were not saturating the PCIe bandwidth even at this point. We're around 70% of PCIe bandwidth. So we are thrashing PCIe. Our algorithm at this point was just completely thrashing PCIe, and in normal circumstances, the performance should have died. But we were getting 2x DDR4, so at 30% chip space. To connect it back to the actual algorithm, we implemented a proof of concept shifting Hamming distance pre-alignment filter. That's a mouthful. It's one of the very old algorithms, very simple to implement. Much better ones do exist, but we were still just learning at the time, so we implemented this thing. And thanks to the increase in PCIe effective bandwidth, we were getting like 30% of the performance we would have gotten if the entire data set was fit inside HBM, even though we were just actively thrashing PCIe at this point. So we were very, very happy about this. And hopefully me and my student, we're working to connect this back into the alignment tool to see if this actually results. I mean, we're fairly certain it will, but we don't know until we try. We will get actually noticeable performance benefit of the end-to-end algorithm. So yeah, we're very excited about this direction. Considering that we probably won't get, Moore's law, different people will give you different answers, but at least in terms of, let's say, DRAM capacity per dollar, it's not going to save us anytime soon. So it looks like we need to actually try to bridge some of these silos so we can do actually deep algorithm application hardware co-design. So hopefully I'm not too over time. Hopefully this is interesting. If you have any questions, I'd be happy to talk. I'm here all week. Thank you.
Thank you so much for the very interesting talk and the very interesting and practical motivation you provided. It was interesting to see the real life story of how these bottlenecks impact people. Questions in the audience? Because I have a question myself. I'm waiting. Okay, so maybe I can get started with mine. So you have a lot of experience and also contributions in two different directions to address the data movement overhead. One of them being the compression-related directions that you presented, and the other one was to bring the computation closer to data, specifically with near flash or in storage processing works. So what are your, let's say, vision about the trade-offs of these two approaches in near-term and long-term adoption and the impacts they could have?
I see. That is a very dangerous question to ask me, because I have drank the Kool-Aid of processing near memory. I'm a fanatic. So if you ask me this question, I will of course say architecturally, I think that is a superior structure, and you know that's how computers should be built. But near storage, near memory computation should be distributed. They should be near the data. Unfortunately. And that's, I think, what we will be working towards. At least my group, we are working towards that future. But at the same time, there's a lot of hurdles in place that prevent people like our collaborator from actually using it for the next decade.
That's exactly why I had the phrase like near term and long term.
Yeah.
Exactly. Okay.
So hopefully there's a lot of problems, as you know more than me probably. A lot of these problems that have to be solved: the compilations, the runtimes, the data movement, all these things. Hopefully we'll work through them, and hopefully my Kool-Aid will not have been for vain.
Thank you so much. So basically, you motivate that direction for long term, while also there are important things that need to be addressed urgently.
Yes. And I think even things like this, they will be useful even if and when we have better architectures.
Yes.
Which I noticed is kind of the title of Onur's talk on Tuesday, I think.
Can we do better?
Yes.
Yeah, thank you so much. It was very interesting.
Thank you so much.
So I'm wondering, are there any questions? Yeah, then maybe we can wrap up. Thank you.
Thank you so much.
I think I believe it's you. No.
Is there any best known algorithm for matching the schemas to reconstruct the sequence and figure out patterns between the KNN?
For de novo assembly?
Yeah.
Normally there's a class of algorithms called seed, extend, and seed filter extend, or sometimes just seed and extend. Normally you would just use a tool called. I do this all the time, I'm sorry.
No worries. You can wear this close to the phone. I'm going to ready for the next screen. Is it? Is it here? So maybe I will disconnect this one so that we can understand. I want to investigation. I will try. Yes. Sorry, we have some setup issue with the results soon. If we try to present it. Okay. This one? Okay, now this is nothing. Where did it go? Oh. Oh, okay.
Oh, finally.
Bio as well. Okay, sorry, there was. Is it? You may. Wait a second. I think disconnected.
Again?
Yes. I think that it's not.
Oh.
Okay, now it's everything. Let's not breathe and move. And hope that things do not fall apart. Okay. So continuing. Jacinto Gomarachi, did I pronounce correctly?
Yeah, it's all right.
Is a senior lecturer at UNSW Sydney. He is also a visiting scientist at the Garvan Institute of Medical Research. His research focus is on developing computational methods for fast and efficient genomic data analysis. Thank you so much, Jacinto.
Okay, so thank you so much. I'll put a timer so that I don't go for like an hour. So, okay, so my topic is algorithms and architectures for long-read sequence analysis. A brief introduction about myself. I did my bachelor's degree in computer engineering at University of Peradeniya in Sri Lanka. Then I moved to Sydney, Australia to do my PhD in bioinformatics. And then now I am working as a senior lecturer, which is similar to an assistant professor position in USA and other places at UNSW Sydney. And I'm also working a lot with the Garvan Institute of Medical Research, where a lot of genomic sequencing happens. So the talk is, first I'm going to give a brief introduction to DNA sequencing. And then I'm going to talk about various computational methods and optimization within 3 areas: portability, scalability, and real time. But first, if all of you know what DNA sequence is, I can directly jump into the actual technical content. Can I assume that? Yeah? Okay, all of you know what DNA sequencing is? Okay, that's cool. So that makes the life easy. So what I'm going to only say is DNA sequencing is very important for all the life sciences areas, especially for health and precision medicine. Like we have all these, domain-specific processes for different stuff. Precision medicine is like medicine that is catered towards the individual's genome, can think of. So DNA sequencing has basically 2 parts. First, the DNA sequencing, and then the associated computational analysis. So if you look at carefully here, something like blood is put onto the sequencer, but before that, it's like, of course, extracted to get the DNA and various chemical processes. But the sequencer is simply a large sensor array that takes the DNA strands through them and measure it in a certain way. It can be like a signal output, a current signal, or some light-related measurement. But here, one step not shown here is the base calling, which converts these signals to ACGT bases, which we call reads. Even though the genome is large, we only read these in terms of little pieces called reads. And these reads have to be put together depending on the application. So typically a bioinformatics workflow has a large number of softwares that are run one after the other, which we call a workflow. And if you go into a single software, it is not just a single algorithm, but a large number of algorithms, heuristics stitched together, which are complicated. And some cases, they may run on a single HPC node, sometimes on a large supercomputing, like a HPC cluster. But the key message is there's no single software or workflow. There are so many depending on the application. And even within a given task, there can be many softwares involved. These are some common, tasks and some example algorithms. But if I put the whole list, it will be like 100 slides or something. So just a snapshot to show that there are some algorithms involved. So now this is how the DNA sequencing technologies and evolved. Like we had mainframes, like here we had these large like sequences. But then the second generation sequences came where it was more automatic. But today we have third generation sequencing like the one shown here. The sequencing machine is even portable. So this is that famous graph. So like in early 2000s, sequencing a human genome costed millions of dollars. But today it's less than thousands of dollars. So as you can see, it has dropped really, really fast compared to even Moore's law. So there had been a huge improvement in DNA sequencing technologies. But one thing we note here is even today, a lot of analysis is typically done on large high-performance computers, even though the sequencing is done on a portable device. Yeah, this has changed a bit in the recent years, but still not all the algorithms and softwares are still capable of being run on portable computing devices. So now let's go into nanopore sequencing. This is the third generation sequencing that also provides portable sequencing. So the sequencer is connected to a computer through USB some interface. We have this thing called the flow cell, which is a consumable which we load onto the thing. That's where you put the DNA sample. And it sequences, and inside it there are hundreds or thousands of tiny little pores called nanopores. That's where the DNA strands go through. When it goes through, it measures what we call the ionic current, a very noisy signal that is indicative of the bases traveling through it. So this signal can be base called, which gives us ACGT bases. And then all those analysis methods I showed you in the second slide can happen. So Oxford Nanopore Technologies, a UK-based company, is who currently produce most of the DNA sequences in nanopore area. So in the portability side, we have MinION, size of a Mars bar, as you can see. And then you have the Promethean, which is like a large printer. This one can do like 48 human genomes in parallel. Okay, so now let's talk about why we need portable sequence analysis. So these MinIONs and like portable devices, scientists previously have taken it to places like the Ebola outbreak to do the sequencing there itself. But the data had to be transmitted over internet for a long time, as you can imagine, to the UK to process, because the data was that large. Similarly, scientists have taken these sequences to space stations and done the sequencing, but still the data analysis had to be done on the Earth due to the size of the data sets. One might ask, okay, why don't we ship the sample? Well, possible, but not always ideal. For example, if it is a pandemic and a quarantine zone, it's not ideal to ship those infectious material, right? So it's better to do the sequencing and if possible, quickly do the analysis there itself as well. And also due to privacy concerns and others, if you can do the sequencing analysis within a hospital, that's also better and also fast. You know, shipping, couriers, missing the things, nothing like that. So doing in situ processing is something we should aim for. So the goal here would be, can we process these hundreds of gigabytes of data coming from a portable sequencer on a portable device like a tablet, laptop, or a specialized hardware architecture that's built. We have done some work in this area over the last few years. I'll go through a couple of examples, just show rather than going into details because the time is limited. So one thing we have looked at is the sequence alignment. Life was made easy for me because the previous talk was about sequence alignment. So the Minimap tool was mentioned there. But of course, here we are using it for reference guided alignment, the other part, not the one for the assembly, okay, complementary. So there's this reference genome that we use to create a large table, hash table, and then we load the sequencing rates. And then we use the hash table in a step called seeding, lot of hash table lookup basically. And then shading, a dynamic programming algorithm to find like probable best matches. And finally, we do base level alignment in using optimized Smith-Waterman and other dynamic programming algorithms. And finally, you have the machine results. So the state-of-the-art tool is called Minimap. So we wanted to initially put this on like edge devices. The biggest challenging was for a human genome, this hash table was too large, like 16 gigabytes of RAM, which is not available on more microcomputing boards. So we designed developed an algorithm and optimization that could reduce this RAM requirement to even 4 GB. So that enabled us to do some alignment on like tiny microcomputing boards like we have shown here. And then we went into the optimizing this tool, and we realized that in genome, like alignment-based method, this chaining is one of the bottlenecks. As you can see, like this yellow part, it's for chaining. So that's the hotspot. So we wanted to optimize this with various hardware architectures to see how much improvement we could get. So we tried using FPGAs, as you know. So here we took this chaining component out and made an accelerator. We relied on high-level synthesis because these algorithms keep changing. So we wanted to have some easy way to change, but they realized it's not that easy to change. So anyway, so we could get like 30 to 90% performance than a multi-core CPU. I think we tested on a 32 core to compare with for a fair comparison. And also this accelerator performance, that seems not that high because we took all the overheads, like copying to the device and back. Anyway, so the key thing was we wanted to keep the accuracy as same as Minimap 2 because changing that means that in downstream applications, we don't know what will happen. So then like we wanted to also use this accelerator in the actual software. Yes, cool, you have the accelerator, but if someone cannot run on a realistic data set, they are of limited use. So we stitched it to the software and then we ran it on FPGAs. And like, yeah, overall, the performance was around 20% compared to running normally. So as you can see, the performance was not like, hundreds of times because those Amdahl's law come into the picture and reduce the overall performance. So this is, I think, a common problem we see in all the architecture accelerators. You have the accelerator, but where does the data come and go, right? So all those components can add up at the end of the day, limiting the overall performance. So, and then we also explored using these RISC-V custom instructions. Again, we focused on chaining here and made some custom instructions. This thing was good, like it gave like 2x performance because it was actually done in the hardware. So anyway, another area that we have been working on is trying to put these algorithms to embedded GPUs like NVIDIA Jetsons. One algorithm used for nanopore signal alignment, slightly different to sequence alignment, but directly do the alignment in the raw signal level. So that we implemented using GPUs. All those like problems like PCI Express bottlenecks come, but we figured out that just doing the backtracing in the GPU itself in a certain way seems to do the things all right. And we got like 3 to 5x overall performance improvement. This is global for the whole pipeline, including the GPU accelerated part. So that was a very good outcome. So the software is still being used by various workflows. And finally, we also demonstrated how we could do certain little like viral analysis on mobile phones, just because like genomes are quite small. And with all the optimizations we mentioned about memory usage optimizations, we could demonstrate that. So that's about the portability. Now let's talk about the scalability side. So a Promethean like this can do like 50 human genomes at a time on a single benchtop. But at Garvan, we have it to like process this data. We need to allocate the whole institute cluster. That much compute. So imagine having 20 such benchtop devices in this place, not that like space required. But to process that data, Australia's supercomputers will have to be allocated. So this is not very practical, right? So we need to be thinking about ways to be able to do these hundreds of terabytes of data processing in a benchtop computer. So we have like done some initial works, and one of the major problems we found out was a I/O bottleneck in nanopore data context. So we introduced a new file format called slow 5 instead of the company's format fast 5. It was ironical because if it's fast is slow, slow is fast. So anyway, the results were pretty good. Just alone by using the file format, we could reduce from days to hours. That was a great improvement. This is on the Australia supercomputer. And as a complementary thing, because of smart laying out of the data, the file size also reduced dramatically. So this is one example of how we try to do the scalability. And the ecosystem around Slow 5 has now grown. We have supported various tools. Others have developed various libraries. And also learning resources. If someone wants to learn a bit about nanopore, like this could be a very good place to start. And finally, about real-time sequencing. Yeah, so these nanopore sequences have the capability of streaming the data, the signal data in real time, but not really many applications can use it. So they just traditionally wait till the end of the analysis and do it. So there's a potential for doing rapid diagnostics if you do this sequencing in real time, but that's not really like used because of this postdoc. So ideally, we would want to like do the sequencing and the real-time analysis in parallel. So one other interesting thing around here is this dynamic feedback possible in the sequencer called adaptive sampling. The next speaker is going to talk about it, so I'm going to leave it to him. So anyway, we initially did some, how do you go back? Yeah, so this is an example work we recently did on making real-time analysis possible for one application called methylation call. And anyway, finally, the key message is, yes, portability, scalability, real-time. At the end of the day, optimized algorithms and optimized hardware, they might be helpful to each other to achieve all these goals holistically. If you improve algorithm, yes, all the aspects are going to be improved. If you have better architectures, all these aspects are going to be improved. So we see a big need for all these like cases. The time to make it accelerated. Okay, so thanks for all my collaborators. I'm glad I finished in 16 minutes and 57 seconds.
Yeah, thank you so much. And again, thank you so much for providing some real life examples because it provides more sense of urgency to see the problem. Okay, questions from the room?
So I would like to know a bit more about the RISC-V extension that you use in one of your projects.
Yeah. Okay, so there we like designed like a big unit for doing this chaining part and made it available as a ROCC instruction, and then use that to do that chaining part of the program. So we simulate, I think we put it onto the FPGA and showed the result. Yeah.
Other questions?
Okay, thank you so much for your talk. I have a question that goes more into your insights about the future. You're working mainly with long reads.
Yeah.
And I wanted to ask your opinion on if they're going to completely replace short reads or you see any sort of hybrid solutions.
I think at the moment it's going to be more hybrid because there are more like certain benefits of second generation short reads opposed to this, and long reads have their own benefits. But I mean, future is hard to tell. These long reads are getting more and more accurate. And if all those benefits of short reads can be captured in long reads, then yeah, it makes sense that one day it might get replaced. But at the moment, there are benefits from the both side. Yeah.
It makes sense. Thank you.
Okay, thanks again. So maybe we can take a coffee break now and come back in 15 minutes. And we continue with the test.
Now,
Yes.
Already?
Yeah.
Oh. Let's say, how is possible to do real time as well? So,
or maybe
so that's like the I get a percentage.
you know, the real reason. And everything and have detection.
They tell you like faces, but oh, okay, so they add another step.
Yeah.
Konstantina, is the mic on? 1, 2, 3, 1, 2, 3.
Sorry, can you speak again?
1, 2, 3, 1, 2, 3.
Yeah. So then we can go.
Just give him a second.
I have a timer as well.
Very good.
Cool.
Konstantina, you can.
Yes, so everyone, we're getting started now. We have our next talk. So I'm very happy to introduce Elton C. He's a PhD student in electrical and computer engineering at Cornell University, working in the computer systems laboratory. His research focuses on computer architecture and hardware software code design for genomics, exploring efficient and scalable systems for real-time biological data analysis.
All right. Well, hello, everyone. Thank you for the nice introduction. My name is Elton. As mentioned, I'm currently a PhD student at Cornell University. And yeah, today I'll be talking more about like the effort towards an edge algorithm hardware co-design framework for nanopore adaptive sampling. So building on top of what Hasindu just talked about in terms of nanopore sequencing. So reintroducing the famous graph. So as stressed by Hasindu, there's a big gap between the sequencing technology and the computation side of things in the genomic world. So over the years, throughout the 3 generations of sequences, we can largely see that there's a huge decrease in terms of sequencing costs, but compared to Moore's law, you know, there's a big gap that we would have to address. So compute needs to catch up, but what we wanted to stress here is that it's not only just the HPC level, but also the edge. And in addition, we wanted to show that, you know, there's been a data boom in the past few years, as you can see from the genome databases. From the left-hand side, you have the DNA, RNA, and then protein. You can see that it has like largely increased. So how do we actually increase the compute so that, you know, we meet the demands of our increase of data? And today's talk will be focusing on the nanopore sequences, which, as mentioned before, provides portable long-read sequencing with real-time analysis capabilities. So a recap on how nanopore sequences work. I'll just really quickly go through it. So at the beginning, we will collect some of our data that we want to sequence. So once we collect these data, samples, we would have to go through a sample preparation stage. And what this does is you put it into some chemical that would extract the DNA within the nucleus of your cell. But during that process, you also get fragmentation of the DNA, which breaks down the DNA into little DNA strand pieces. Before you do the sequencing, you would have to go through another phase called library preparation. In this stage, you would have your little motor proteins attached to your DNA strands. And these motor proteins during the sequencing stage would basically swim towards your nanopore on the flow cell right here. And once the motor protein attaches to the nanopore, it starts feeding the DNA strand through the pore, and you can capture the RNA current trace. So this trace is accessible during runtime in real time on your host PC that connects to MinION. And once you finish your sequencing phase, your usual post-processing flow will look like this. So you get your squiggles, which is the raw nanopore signals, and then you do base calling, which converts the squiggles into a GCT format. And we have your base reads. And then you can go nuts with whatever your favorite post-analysis tool is, whether it's Minimap2 or whatever. And from mentioned in the last talk, you know, there's been cases of using nanopore sequences in very unique fields that previous generation sequences has never done before. For example, you know, surveilling Ebola outbreak in West Africa, and also, you know, sequencing DNA on the International Space Station. However, all of these, after sequencing, you would still have to transfer your data back to somewhere else to do your processing, which kind of loses the whole, you know, purpose of portable sequencing, because why not just collect your sequences and go back to your wet lab and do everything there? So one thing that I wanted to stress out is the feedback loop that Hasindu briefly mentioned, but didn't go into details. So on the left-hand side, we have what we just saw, which is the flow of sequencing. Once you collect your data and you do your post-analysis, let's say you're doing in-field sequencing during an expedition that takes 7 days. You wouldn't want to wait for 7 days to get your data back and then realize after post-processing that you sequenced the wrong thing. So one thing that you really want to do is being able to do analysis in the field after you sequence it, and then look at the results, understand what the results are, and basically adjust your experiment or sequence target based on the results. So that feeds a feedback loop back into the sequencing flow. So that's the first feedback loop. But the real-time analysis capabilities of nanopore sequences also provides a very interesting, unique capability, which is real-time analysis and rejection. So what this means is that during runtime, if I'm doing an experiment that I'm only interested in parts of the region of a whole genome. For example, if I'm studying cancer and I don't care about anything else, like any DNA that goes into regions that's not the cancer regions, then what I can do is I can focus my sequencing efforts on the parts that's our region of interest, ROI, and reject anything else. So the rejection goes back into the MinION sequencer, and that would basically reverse the voltage at the individual nanopore channels and basically shoot out the DNA strand and skip to the next one. So this poses like two very unique feedback loop that enables adaptive sampling from the sequencing side and your experiment side in the field. So the outer loop is roughly in the scale of hours to days, and then the inner loop is roughly in the milliseconds to seconds. And today's talk will focus on the real-time analysis part, which is the adaptive sampling. So I briefly talked about targeted sequencing, but the definition of targeted sequencing is basically we focus our sequencing efforts on regions or organisms of interest instead of reading everything like whole genome sequencing. So traditionally, you would probably do something like an amplicon sequencing situation where you use PCR before you do the sequencing. You do some extra step to amplify, the targets that you want. But although this is fast and inexpensive, this is very limited to known regions of your DNA. The other method is called pull down, which is more flexible, where you could sort of define which target you want to enrich, but it's also more costly and takes a lot of time for preparation. So it's not really feasible in the field. And for nanopore sequencing, with this like feedback, you basically make this targeted sequencing a compute problem. There's no pre-sequencing preparation, and you basically use software to define your criteria to filter out what to sequence and what to reject. And one thing I want to stress is that compute becomes very important in this case. So redrawing the feedback loop for just the adaptive sampling part, we have the DNA go into your nanopore device with your laptop that collects the data, and then you have some real-time analysis blob, which makes some decision and feeds back into the DNA itself. In terms of timing, if we're not doing any adaptive sampling and we're just simply sequencing the whole DNA strand, let's say this is roughly this amount of time, so T read sequence time. What about read until timing? So read until is the protocol for the adaptive sampling for Oxford Nanopore. So read until, you would have an extra compute to do some computation to decide whether you want to reject it or not. So what would happen is usually you wait for a little bit of time, let's call it T collection, to collect enough data for you to do your computation. You'd send this data to offload this to do compute. And while you do compute, the sequencer also continues sequencing your data. Let's say after T-compute, we decided, okay, the current read is not of interest and we want to reject it. We would send a rejection back. And basically the delta between the T-read sequence time and the collection plus compute time is essentially the time we save. So the more time we save, the higher percentage of the region of interest we would have in our resulting data, which means we have a high enrichment. Now, this poses a very interesting trade-off. So if we wait for a little bit longer for collection time, then we basically leave less space, less time for us to make our decision, which means our enrichment would gradually go down. However, if we wait longer for the collection, we also have more context for us to do our mapping, which means our mapping accuracy, our decision-making can be more accurate. But at the same time, with more context, you have more processing, and like alignment algorithms are usually pretty bad in terms of like complexity and time and space. So this sort of like poses a very interesting trade-off. But in addition to that, we also have the reality where we actually don't have that much time to make our decision. So in reality, what happens is that if you reject a read a bit too late, that's like deep inside the pore already, what happens is that it would possibly clog the whole pore, which means your whole sequencing flow in the next like for the rest of the experiment, you basically can't use the port anymore. So yeah, just to give a feeling, the time requirement is roughly around 5 to 7 seconds for DNA. However, you have to also consider that for a mini device, you also have a bunch of different channels. So that's like 512 channels all going in parallel. So there's a lot of data for us to compute. So how do people actually do the computation? So adaptive sampling analysis flow typically goes into two types. The first type is base level adaptive sampling, where we want to use like our well-known tools like Minimap or tools that we've studied a long time that basically does your analysis in the base domain. To do that, we would take our reference genome and we want to do some mapping against this reference genome, which people have done before. And as mentioned earlier in the talk, it might be 99 point something% similar, so we could just trust that this could be a reliable reference. However, our reads come in as squiggles, which is signals. So in order to do base mapping, we would have to do real-time base calling on the squiggles to convert it to base reads. And this poses a problem where in order to do the base mapping and do the real-time base calling, we would have to use GPUs that's a bit more powerful. So roughly in the, desktop, at least the desktop ranges of NVIDIA GPUs. The other kind of method would be directly working the squiggle level. So instead of doing the mapping in base domain, what if we just skip the base calling and try to do the mapping? So we have our squiggles directly in the squiggle space. That's good. But what about the reference? So in order to do the mapping here, we would have to convert our reference genome in the base domain directly to a squiggle domain in a synthetic reference. And to do that, we basically have these K-means models that you could slide through and basically have pre-trained data that would fill in the gaps, which gives you sort of like a synthetic low noise representation of what your AGCT reference looks like in the signal domain. So after that, you would get your results. But the thing is that both of these usually run on HPC, and if you really want to do like selective genome sequencing in the field, that's not really possible. And so we want to really move to the edge. And how do we do that? So in 2023, we published this work called Haru. It stands for Hardware Accelerated Read and Tell. Essentially, Haru is a hardware software co-design framework. We designed an end-to-end analysis framework that could get reads from I/O and then do some mapping. And then we also basically target edge SoCs that also has FPGAs. So the device that we targeted is the AMD Xilinx Korea KV260. I think the price has gone up a bit, but it's still like sub $300 USD. And basically it has a quad-core ARM processor as well as a FPGA co-packaged together. So basically the idea is that we could give it, we could have the pre-compiled bit stream somewhere hosted, and researchers can just spend, minimum amount of money, get the board, run the code, and have high speed up in the field. And but I wanted to point out that this is not just the only way, and I want to use this opportunity to urge everyone to go look at the SMX paper, which is a work that we did in collaboration with our colleagues at Barcelona Supercomputing Center, where this is more also sort of like directly integrating ISA extensions and co-processors inside CPU designs so that we could do universal sequence alignment in a fast way. But in this context, we're still going to stick with FPGAs and talk about like acceleration for this. As mentioned, we're going to skip the whole base calling part, so we would have to operate in the squiggle space. And the challenge here is that we would have to have alternative algorithm to do our alignment part, as opposed to the classic algorithms that we sort of love and hate at the same time, which is the two Smith-Waterman and Needleman-Wunsch, if I pronounce it correctly and didn't butcher that. But one's basically a global alignment considering the start and end positions being at the start and end of the Korean reference, and we try to connect together. So you could do a lot of optimizations like banding and stuff. Smith-Waterman basically tries to look at like the local subsequence match, and these two basically operate in the discrete space. So you have like symbols, AGCTs in particular. However, like instead of like explaining what DCW is, I'm just going to directly connect the dots. DCW and subsequence DCW is basically the temporal version, like time series version of Needleman-Wunsch and Smith-Waterman. So basically one's for the global and one's for local. And in this case, we want to directly use subsequence DTW to quickly search where the subsequence of your query, like where your query matches the best on your whole reference. So to do that, we basically, first of all, we couldn't do banding in this case because we're considering all the samples in your sequence Y, which is the reference, as potential starting points. In this case, what we did is we designed a PE chain of elements where each of the chain will compute one cell inside the matrix, and all of them can be done in parallel because all the dependencies are ready. So you have this wavefront of PE chains sliding through the reference and doing the computation fastly. And on the bottom side, we have the whole flow where we have the the sequencer generating the reads to our ARM core. Our ARM core would do some pre-processing to reduce sort of the signal space to less samples, and then we'll stream it to the FPGA to do acceleration in a SDTW accelerator. Now, in terms of evaluation, we sort of compared it with two different sets of evaluations. The first one is, let's compare apples to apples. So let's just do subsequence DTW only. Everyone does subsequence DTW. The first work we have is RUscripts, which is the first Python-based implementation that showed that subsequence DTW works well for adaptive sampling. But since it's Python-based, it's not really fair. So we also provided a multi-threaded C implementation that still only does subsequence DTW. And then for the Haru part, we basically replaced the SDTW calls to the accelerator. We have 3 different platforms that we run on. This is mostly just to motivate how we jump from more resource on the high HPC level to a desktop, which is more edge, but still quite powerful, and then to our SoC, which is the Korea board that has the ARM plus the FPGA. And as mentioned by Hasindu, all of these throughput and timing includes all the overheads of hardware to software and all the I/O and stuff. So on shorter references, so for example, the COVID-19 SARS-CoV-2 reference, you can see that Haru really outperformed all the different the 2 works on different platforms. But if we go to a larger reference, which is still not that huge, but a partial human genome larger than the COVID reference, we still get a lot of speed up, but if you compare the actual reads per second, it's actually not that impressive anymore. So this shows one of the downsides of the current work of Haru, the prototype, being limited to not scalable towards your reference size. But just within the context, you can see if you map out like the energy efficiency, which is like how much energy you spend to process one read, and then on the x-axis you have the time to process each read. Haru is actually really nicely close to origin, which is like for each read, we spend a very minimal energy and we're fast, which is what we want out of hardware software co-design, and this is perfect for edge situations. We also did some evaluations of a bit apples versus oranges, but this is mostly looking at these subsequence DTW based, like only alignment based methods versus other methods such as a neural network classifier that basically just predicts you take a squiggle and then say whether this belongs to a region or not. We try to run all of these on like platforms that's edge or better. So mostly just showing that Haru, even though it's running on the edge, the throughput's still higher than most of them and the accuracy is nice. But the second one is the well-known real-time base calling plus real-time mapping through Minimap, and we ran that on a Jetson Xavier, and we have Uncalled, which is a work that does signal space indexing, which doesn't do alignment. This is just a really quick run through of like the Haru work, but just before we end the talk, I'll talk about some of the ongoing sort of efforts and ideas that we've been looking to extend Haru. So the idea for Haru is to have a modular, extendable hardware software co-design framework. So we don't want to just limit to SDTW acceleration. So the first thing is to look at what are the other ways for us to do efficient squiggle mapping in the squiggle space. And one of this work is called Rawhash from Safari Group. Does seed and extend in the squiggle space, which is kind of interesting because you basically can have some sort of fingerprint out from the noisy signals itself and then efficiently map to your hash table index to get anchor points for you to extend on. So one of the work that we've been extending, unfortunately we didn't have like preliminary results today, but one of the ideas is basically with the seeds, we would still do DTW calls. So no longer subsequence DTW, but DTW. And then we would basically extend on those and compare the scores of the similarity. So that's the first step. And the next step is basically we want to move towards having more of an accelerator zoo for this adaptive sampling framework. So we could have, now we have the alignments accelerator, but we also want chaining or maybe event detection or real-time base calling, all as possible choices. And then with that, we want to leverage the space we have on the FPGA and have multi-accelerator deployed on the design. So the Korea board that we use, which is from AMD Xilinx, basically there's two ways of doing your FPGA development. The first one is a flat design where you have full control over the whole fabric and you would synthesize everything and then reconfigure the whole fabric. The second one is basically called dynamic function exchange, where you basically have this static shell and then for the rest of the area, you're slotted into individual slots. And you can do partial reconfiguration to swap out like individual slots to replace with the bit stream that you want. But one of the idea, this is sort of like a preliminary, which is, let's say you have a really long processing pipeline and you have different stages. All of them takes a long time. And you have like different sets of accelerators that you want to apply on. So maybe you're at stage 1 and then you can preload the stage 2 accelerator. And then once you're done with the stage 1, you no longer need the orange accelerator anymore. So you could swap it into, let's say, the alignment accelerator. And basically in runtime, you swap out the accelerators to match your need throughout the whole runtime of the application. So that's one of the ideas. And of course, being edge device, you could easily scale up your device by having clusters of your Korea boards all doing work at the same time. But yeah, so these are sort of the ideas that we have. And I want to acknowledge a lot of people, including Hasundu and the team at UNSW, as well as at Cornell, and also the reviewers for the Haru work and Garvan Medical Institute. And yeah, that sums up my talk, and I'm ready to take any questions.
Thank you so much for the very interesting talk. So regarding the accelerator zoo that you mentioned, or like looking at different stages in this domain, it's definitely very interesting. And we have recently a paper from our group called RawBench, which is a benchmarking framework to look at different stages of nanopore signal analysis. So it might be useful to profiling some of the different tools for your goal.
Yeah, I think I started the repo. So yeah,
Okay,
yeah.
cool. Nice.
Very interesting work. Yeah.
Okay, questions?
I actually have one.
So what I find really interesting is this idea you have about your future work about instantiating multiple accelerators on the FPGA. And I think it is indeed very challenging to be able to utilize the resources and don't have underutilization. So I wanted to ask a little bit if you have thought about how many instances of each accelerator you would instantiate, how you would do the workload balancing, communication of data.
Yeah, so this is a very preliminary idea, but in terms of, so previously we did look at sort of the alignment accelerator and instantiate multiple alignment like SDW accelerators. From the area, we could safely instantiate 3 of the SDW accelerators. 4 might work, but it really depends on the EDA tools and the efforts on optimizing the path for timing. So. But that stays with the flat design. For the other ones, it really comes down to how big your design is, and if especially if you're doing like the slotted DFX situation, there's even less space for each slot. So I think it really comes down to the hardware design at the end. Yeah.
Yeah. I think it's very interesting, and it would be, I think you would get the most benefit out of some sort of dynamic scheduling of these things.
Yes.
I myself also often in designs and supervisions, I think I've been bottlenecked by these.
Yeah.
Because like each step runs in a different throughput.
Yep.
And you will end up with idle things if you schedule them statically.
Yep.
So I think it's a very interesting thing to work around.
Sounds very good.
I look forward to seeing what you do.
Also sounds like a hard problem as well.
Yes. Okay, I think we're good. We can go with the next. Yes.
No more questions. move with the next talk. So we will use his own laptop.
Yes, great, thank you.
And now let's move everything, hoping nothing falls apart.
You can come this way maybe for a brief bit, so move them to the side. Please.
It's okay.
It's okay, it's okay.
Anywhere you can.
It can come here.
So now you try sharing your screen when you're ready.
Do you have a USB port to use this? No, you don't have to. You can use your
use your laptop. It's okay.
Whoops. So I have like other adapter for this bit.
If you're okay with your laptop to keep, are you okay with that?
Okay, yeah.
Otherwise, we can set you off.
So let's first fix the sharing.
Yes.
So what you can do here is go on here and slide and hide the maybe over the speaker.
You could hide
This
video
video panel.
Okay.
and then hide the floating meeting controls.
Yes.
Okay,
So that this is full screen. It's on our side. In the meantime, you can wear this so that we capture your voice. It has a flip.
Oh, see. Actually, just sorry.
So you stop sharing, right?
Yeah. Just one promise. Is it?
There.
Yeah, not this one, not this. I'm sorry, but is it? No, I mean, it seems that my presentation slide is just mirroring to the slide. So, can I use this? And then,
I don't think you can do it with one screen.
I think it's
Maybe presentation.
So you
Oh,
want
I think it's okay.
Okay, great.
Okay.
Good. Yeah.
Okay.
Do you want to read his bio?
Yes. Of course. Okay, I'm confused. Sorry. Okay, so everyone, we're ready for our next talk. Sorry for the small delay. So let me introduce you, Sing Han. He's a PhD candidate at Ghiasi, South Korea. His research interests are domain-specific accelerator architecture for emerging applications and hardware-software design for end-to-end systems.
Thank you for nice introduction. So good afternoon, everyone. My name is Sing Han from Ghiasi in South Korea, and I'm really honored to have the opportunity to share my experience in this live workshop. Today, I will present with the topic named the From Genomics to Proteomics, Architecture Solutions for Memory-Intensive Health Applications. I like to address the memory bottlenecks that limits today's health-related applications. So let me start my presentation. Since the name of this workshop is Architecture for Health, so let me start with the keyword health. So throughout history, people always pursued one thing, the good health. So to overcome disease, to live longer, or to live better lives, the health always has been one of the most fundamental of humanity. In the past, but we relied on lifestyle improvements or medical treatments to maintain our health. However, such approaches only treated the symptoms, not the root causes. However, but today, with rapid advance in bioinformatics and artificial intelligence or AI, we can analyze biological phenomena in much detailed level. Let me give you some example of this one. So for one case, I think many of you heard this many times today, but DNA sequencing decodes the generic sequence, helping to identify generic information and get insight into the genetic origin of disease. And for other case, I think this is the first time come out this workshop. The protein structure prediction model predicts the 3D structure of proteins, helping us understanding the molecular mechanisms and interactions of proteins, and also discovery of new functions and potential drug discovery of new drugs. I'm sorry, I'm a little nervous. So these two kind of like technologies have shifted healthcare from treatment to understanding the root cause of disease and also accelerate the personal drug discovery. However, as these models become more sophisticated, these applications demand enormous memory accesses. So there are two main reasons of this. The first, the biological data itself is really massive. So for instance, the human DNA has nearly 3 billion base pairs, and even single protein structure has thousands of amino acid interactions. It's really hard to model it. And the second reason is that AI model amplify this demand. Recent AI models used in bioinformatics models has billions of parameters and massive activations. And as everybody knows, the memory access is becoming the main performance bottleneck of this kind of AI models. So as a result, these like modern bioinformatics models are now not compute bound, but memory bound. So memory demand is a really critical problem because it limits how much biological information model can handle through the same model. To tackle this issue, I'd like to introduce two cases from my research to discuss how memory bottleneck emerges from recent biological models and also how our team handle it. So first case is DNA sequencing announced on this ISCA 2024 named BLAST. And the second case is the protein structure prediction model, in short PPM, announced on ISCA 2025 named Light Novel. So given the limited time today, I'll focus on delivering the key ideas of my researches clearly. So if you're interested in my presentation, please refer to my paper. Okay, let me start with the DNA sequencing. Yeah, I know that last presenter asked you, and I think everybody of you already know what DNA sequencing is, but let me introduce very simply what DNA sequencing is. So DNA sequencing is the technology that determines the order of nucleotide base pairs, known as ATGC, constituting the DNA chain. It has really critical role in identifying the mutations on genetic disorders and infectious disease. But unfortunately, whole DNA cannot be read at once due to technological limitation. So modern techniques such as next generation sequence or NGS breaks DNA into small fragments named short reads and then read them separately and then merge them to reconstruct the full sequence. I heard that the last presenters are like focusing on the long sequence alignments, but when I was focusing on this research, the short read alignment was the state-of-the-art technology. So I think it must maybe interest to know about short read alignment. Yep. But to do this, to merge and get the full sequence, every short read must be aligned to the reference genome sequence from the human reference genome is already known. So all short read must be aligned to the reference genome sequence under specific conditions. This read alignment step dominates the read alignment, the total runtime of read alignment, often taking more than 80% of the entire sequencing pipeline. Okay, let me show the simple animation about the read alignment. So in read alignment, short reads are arranged into the reference genome. So this process consists of two steps, so seeding and the seed extension. So in seeding step, each part of the short read is compared with the all location of the reference DNA positions. So yeah, look like this. And this comparison is repeated for every short read. And then the matching results are called super maximum exact match or SMAM. The name is not important. Then the seed extension is conducted in which SMAMs are extended on each side. And then merged together. Analyzing the minor difference between the reference genome and our new aligned sequence can explain that given DNA-related phenomena. Here, lots of memory accesses occur during the seeding process for computations. So in this work, we focus on the seeding process. Yeah. So in seeding, we need to come, as I told you, in seeding, we need to compare each short read to the reference genome to find the most similar position. But because the human genome has billions of base pairs, this process involves an enormous number of memory accesses, making it memory intensive and bandwidth bound task. So a naive comparison method of every possible position is simple, but it's clearly inefficient. So most systems use additional index data structure to simplify the search process. So recently, the learned index has emerged as a new index data structure to assist the search process. The learned index is a simple machine learning model-based index structure that saves the guaranteed range of sequence location in the suffix array. It helps narrow down the candidate region, after which a small binary search is applied. As you can see in this picture, if you want to find CA in the total sequence, the learned index model helps us let us know that the CA is in that small red bound, and we can do binary search to find where the CA is. Furthermore, to find the multiple positions with same similarity, we need to do some additional exponential search from the result position of binary search. Yeah, even we have index data structure, but every iteration of binary or exponential search needs additional two external memory accesses. One to the suffix array to find the location where the reference DNA exists, and the second memory access to get the real reference DNA from the memory, which is to be compared to the short read. But because the accesses are random and scattered, the memory traffic quickly becomes the bottleneck. To migrate this problem, we introduced a coarse-find block data structure. We divided the suffix array into two groups and co-locate the additional suffix array or partial reference DNA segments with the same memory line. This enhances spatial locality between suffix array indices and reference DNA segments. This is one example case that how spatial locality can be utilized. So this co-placement allows some accesses to be served from the data which is already fetched from memory. For example, in this case, the reference DNA does not make any more memory access. So it saves the almost 50% of memory access in this case. And next, we exploit the temporal locality with the algorithm named guaranteed search range update algorithm. It maintains 4 pointers that reflect the information from previous search, dynamically shrinking the next search range. For example, in the picture below, assume that color, it does not see well, but blue and yellow positions are already known with the previous searches. Then we can know that some reasons with the gray arrow is the known reason that we do not have to search again. We already know that some positions are already included in the result and some positions are already known that not to be included in the result. So we have to do search in only the red arrow region, which is really narrower than the conventional search area. So compared to the conventional method, this area is small, which means that memory access can be reduced. Building on these ideas, we designed a specialized hardware accelerator named BLAST. So BLAST consists of seeding core scheduler, memory interface, and high bandwidth memories to maximize the memory bandwidth utilization and exploit locality at the architecture level. So as a result, BLAST achieves up to 35 times speedup over conventional systems, processing 134 million reads per second on human genome datasets. Okay, this was about the first case, and let me move on to the second case, which is protein structure prediction model. So as everybody knows, proteins are the fundamental building blocks of life. So from skins and hairs and hormones and enzymes, everything are proteins. So although proteins are linear sequence of amino acids, they fold into like complex 3D structure called tertiary structure. This 3D, in detail, this 3D folding structure determines how protein interact with other proteins. They bind selectively with other proteins which has like compatible shapes. Hence, so finding out protein structure is critical for biological and pharmaceutical applications. However, experimentally figuring out the 3D structure of protein is really slow and expensive. To address this problem, recent advances have turned to prediction with AI-based computational models. Models such as AlphaFold from Google or ESMFold from Meta are representative examples. Last year, their impact has been recognized with the Nobel Prize in Chemistry. These models achieved remarkable prediction accuracy compared to the previous model, demonstrating that it has potential of replacing conventional experimental methods. However, there emerges another problem that these models suffer from massive memory consumption. This is because the activation tensor named pair representation, which captures amino acid interaction, has a really large dimension compared to conventional AI models. So as you can see from this graph, its size grows quadratically with the sequence length, and it leads to out-of-memory errors, limiting the sequence length that model can process. To overcome this problem, through activation analysis, we observed that protein activations exhibit small variance between channels and large variance between tokens. This tokenized characteristic motivated tokenized quantization, where scaling factors are shared per token, along with additional outlier handling to maintain accuracy. We divide activations into 3 groups based on tensor-wise value distribution. And then we apply different tokenized quantization schemes to each. We dynamically apply low precision for inliers and adjust the number of handling outliers depending on their characteristics. To efficiently soft our purpose method with maximize token level parallelism and minimize memory access overhead, we designed a special hardware named LightNovel. So it is built around 2 main units named Reconfigurable Matrix Processing Unit, or RMPU, and Versatile Vector Processing Unit, or VVPU, to leverage benefits of token-wise quantization. As a result, in accuracy, LightNovel achieves less than 0.001 drop in TM score, which is an evaluation metric for protein 3D structure, and it is negligible. Also, in end-to-end performance, LightNovel achieves up to 141 times speedup compared to recent NVIDIA H100 GPU over existing protein structure prediction models. Okay, let me conclude this talk. Okay, to summarize, modern bioinformatics applications are no longer compute-bound, but memory-bound. Also, each application exhibits unique data formats and access patterns. Our approach is a software-hardware co-design that jointly optimizes the data flow and memory hierarchy, and also apply the lightweight algorithms such as quantization. This kind of approaches not only improve efficiency, but also enable new biological insights, which are previously unattainable due to technical limitations. At this point, I believe that the domain-specific accelerator, or also called DSA, can be an effective solution for bioinformatics applications. This is because the domain-specific accelerator can provide optimizations tailored to each application, and by exploiting the data regularities and access patterns, domain-specific accelerators can dynamically reduce memory bottlenecks and deliver much higher efficiency than conventional general-purpose processors. Ultimately, I believe that the connecting bioinformatics and computer architecture will shape the next generation of health-oriented systems. Okay, thank you for your attention. And if you enjoyed the talk, please take a look at our paper for more details. And I'm happy to take any questions.
So thank you so much for your presentation. Any questions in the room?
Great. I don't think this will.
That's okay.
It's now.
Thank you so much for covering these two interesting directions in your talk. So I have two questions. The first one is, do you know the impact of software versus hardware in your optimizations for the second work? How each of them individually provide benefits?
You mean in the like PPM? So my software idea is to apply quantization in the PPM model, and the hardware is to like efficiently support the software. So in accuracy and like memory consumption, almost all the advantages from the software. But even though we use quantization, you know that in modern hardware, general purpose hardware such as GPU, the quantization is really not compatible with that kind of hardware. So we believe that these kind of quantization schemes cannot be efficiently done in GPU. So even though like most of the advantages come from the software level, we need hardware to efficiently support that software.
Okay, yeah, thank you so much. Yeah. And maybe I can keep also my next question for after the session because we're already running a little bit late. But yeah, it was very interesting topics. Thank you so much.
Thank you.
Okay, so the next talk will be myself. Okay, thanks.
Do I use this? Okay. Okay, yeah, I made it over here, so.
Thank you.
You use which one?
Both of them.
Both of them?
This for Zoom, this for Zoom.
Wow, okay. You can see how complicated it is to live stream these things. Anyway, I'll hold both of them in my hand. So I'm not going to be here for so long. Thanks for attending this first incarnation of the Arch4Health workshop. I was online to introduce it, but it's great to see everyone here. We hope that this will be a bigger and bigger workshop and maybe at some point a conference over time, because we believe this is one of the most important topics that is going relatively, in my opinion, unnoticed. I should also say to the previous speaker that don't be ashamed of working on short read analysis. Short reads are still extremely important. This is something that I think architecture folks also need to realize. It's used in many medical settings, short reads. Even though long reads are very important also, short reads are not going away anytime soon.
Thank you.
And maybe there will be hybrids that are coming up going into the future. So I sometimes see, for example, people reviewing papers saying, oh, your paper is on short reads, reject. That's a terrible thing, right? I think that's saying like, your paper is working on GCC. It's not a workload that is important anymore. So hopefully that gives you, so don't be ashamed about working on short reads. You're doing great work, I think. Keep going. So yeah, I don't want to take more time. If you're ready, I'll introduce Nika. Well, Nika, you know, she's one of the organizers. She's my PhD student, probably the next one to graduate, hopefully, sometime next year. And she's been working on architectures for bioinformatics for a long time, especially on storage-centric architectures for bioinformatics. And she was quite enthusiastic to organize this workshop, and I couldn't say no. Even though there's a lot of things that I had to do, I think this was also very important to do. And she's going to be on the job market next year, looking probably for academic positions. And she can tell you a lot of stories on storage for genomics and metagenomics, and also emerging technologies like 3D stacking, monolithic 3D integration. That's an area that she has been working on separately. And maybe there's a nice combination of emerging technologies, especially with these earlier talks that have variable devices. I think we cannot keep the form factors that we have been using in general purpose technologies. So emerging technologies like monolithic integration, monolithic 3D integration are actually very fascinating for health, in my opinion. Okay, I'll leave it to Nika, and thanks for attending again. What do I do here? Okay, she gets the.
Yeah. Yes.
Oh, yeah.
Is it? Do you hear it if I just put it on the table? Or like I will hold it as well?
Yes, we can hear you.
Okay. So I'm going to talk about my research and the research we've been doing in the group around the storage-centric systems for genomics and metagenomics. So as we have heard at multiple times today, there are many critical fields that genomics and metagenomics play critical roles in, such as uncovering and treating diseases, developing personalized medicine, detecting pathogens in the environment, and rapid surveillance of disease outbreaks. And as we've learned today, and also maybe knew before, a lot of these applications and many more depend on and rely on understanding the information of DNA of organisms that we have in samples. So and based on the similarities and differences of this information in the sample's DNA to other samples or to some reference genomes, we can make medical or biological conclusions to guide these applications. So the information that is encoded in the DNA gets translated to digital data by these high-throughput sequencers. So we have seen again different types of them and being analyzed and being elaborated in today's workshop. And as we have seen, the current sequencing technologies cannot sequence very long DNA molecules end to end, and instead they extract the smaller fragments of the original DNA sequence known as reads. So therefore, a lot of these genomic applications rely on this key step that is called read mapping to map these reads to a reference genome and align them there and find the similarities and differences that these reads have compared to this reference genome. And that is computationally challenging because we might need to leverage computationally expensive approximate string matching algorithms. And this complex computation needs to happen on large amounts of data. So basically what happens is that these applications therefore suffer from computation and data movement overhead. So now what is metagenomics? It refers to study of genome sequences of diverse organisms that are in a shared environment. And this can be blood, human gut, ocean, soil, etc. And the benefit it has is that it overcomes the limitation of traditional genomics in scenarios that we cannot separate different organisms to analyze them separately in the lab. So therefore, metagenomics has led to groundbreaking advances in many fields, such as precision medicine, understanding microbial diversity of an environment, and discovering warning signs of diseases. So since the organisms that are in the metagenomic sample are not known in advance, metagenomic analysis typically requires performing several steps to understand what is in the sample. So I'm here going to show the DNAs of different organisms here. The first step typically involves preparing these input queries and extracting some shorter sequences of length k out of this input data that are called k-mers. And then look up these k-mers in a large database that contains information on many different species. And by looking them up, then we can see based on their intersection that what's in the sample. And the size of these databases can be very large. In some emerging cases, it can exceed 100 terabytes, and they grow at a fast rate as we get to discover more and more organisms in microbial environments on Earth. So after detecting what are the species that are present in the sample, there's also optional steps such as figuring out what's the relative abundance of these organisms in the sample. So the problem we have with genomics and metagenomics, as we have also heard today with some very interesting real life examples, is that we have these fast specialized machines to generate this data, but then relying on general purpose machines or just scaling these general purpose machines more and more would be inefficient and slow because we have a lot of computation and data movement overheads that we need to deal with. And because of the importance of this domain and the problems that it is dealing with computationally, there's been a lot of effort to make it faster, including coming up with a specialized hardware in also industry and looking at both industry and academia. All these efforts led to nice ideas and designs to come up with new heuristics, accelerators, or some filters to reduce the computation burden. And they've actually have been showing promise to alleviate computation overhead. However, we are still facing with the data movement overhead from the storage system, whose impact on end-to-end performance actually becomes even more pronounced as other bottlenecks such as computation and main memory get alleviated. And as we also had an interesting talk earlier before the coffee break that Sang-Woo talked about one approach of compressing data to alleviate this overhead. But in this talk, we will also look at another angle that can be used and also in combination together to with the other approaches that we learned earlier to alleviate this data movement overhead. So what I want to do in this talk is to summarize and make a case of what storage-centric system can do in these data-intensive domains by talking about our work on storage-centric systems for genomics, metagenomics, and some emerging areas in this direction that we've been focusing together as a group. And before I conclude, I will also talk about efficient analysis on compressed genomic data a little bit. So let me very briefly summarize what we did here for genomics in our work GenStore. So the key idea we had was to filter reads that do not need that heavy-duty computation for alignment inside the storage system, and only move the reads that need to go through more heavyweight computation. And some examples would be exactly matching reads. As we have also heard before, we have a lot of similarities in genomes of organisms, specifically if we consider short reads, there will be many exactly matching reads. And in cases of long reads or short reads, depending on organism and use cases, there might be also several non-matching reads. One of the important use cases for non-matching reads would be contamination filter. That is a critical step. So anyway, there are also more details about these scenarios in the paper, but what I wanted to also emphasize is that although this can be very beneficial, but there have been a lot of design challenges, such as the fact that read mapping workloads can exhibit very different behavior across different data sets and use cases, and there are limited hardware resources in the storage system. So we had some hardware software co-design approaches to tune the algorithms and approaches to these specific hardware constraints of the storage system. And we proposed GenStore, which are basically very lightweight filters inside the SSD to filter reads that do not require alignment in the SSD itself. And it helps alleviating computation overhead by filtering the reads, but also helps alleviating data movement overhead right from where the data is originally residing. And we showed that this very lightweight structure actually can provide this significant speed up and energy reduction at low cost compared to state-of-the-art software and hardware baselines. So there are a lot more details and results in the paper. So if you're interested in the direction of storage-centric systems and what they can contribute to this domain, please check our paper. And now I also provide a very brief summary of our work on metagenomics. So this was the pipeline of metagenomics that we went through a few minutes ago. Because this pipeline accesses large amounts of data, we performed a case study of performance of metagenomic analysis tools with various state-of-the-art SSD configurations. And we observed that compared to an idealized scenario with no I/O overhead, there's a large performance overhead from performance optimized and cost optimized when we use in the system performance optimized and cost optimized SSDs. So this data movement, of course, then, as we see here, leads to large performance overheads, and we observe that it becomes even more serious problem when we leverage some existing accelerators to perform the computation. So by addressing other bottlenecks, as we discussed, I/O even becomes more prominent in the end-to-end, like the impact of it becomes even more prominent and maybe an urgent problem to look into. And actually, this I/O overhead to access large amount of low reuse data is very difficult to avoid. One might consider sampling technique to shrink the database size, but that can lead to accuracy loss to levels that will be unacceptable to many use cases, specifically in this field, as we can imagine, accuracy is one of the prominent design factors and critical. So, and the second potential solution might seem to be keep all data required by metagenomic analysis completely and always resident in main memory. But such solution, we believe, is energy inefficient, costly, unscalable, and unsustainable because these large databases that are already, as I discussed, can be very large, are increasing in size rapidly, roughly doubling every few months. And the second point is that different analysis need different databases. So it would be very inefficient to perpetually keep all different databases that we would need for various different types of analysis in main memory at all times. So motivated by these points, our goal is to improve metagenomic analysis performance by reducing data movement overhead from the storage system in a cost-effective manner and with high accuracy. While processing data directly inside the storage system can help us alleviate the data movement overhead from storage and achieve our goal, but it's very challenging because no metagenomic analysis tool can run inside the storage system due to limitations of SSD's hardware, such as long latency of NAND flash chips, limited DRAM capacity inside the SSD, and limited DRAM bandwidth inside the SSD. So our work MIGIS is the first storage processing system for end-to-end metagenomic analysis. Then its idea is to have cooperative storage processing for metagenomics, which is enabled by hardware-software co-design between the storage system and the host system. So to effectively leverage capabilities of both systems and also coordinate computation between them, MIGIS has hardware-software co-design in 5 different directions. First is task partitioning and mapping, such that each step executes in its most suitable system. I won't go through the details of how we do the mapping because of the limited time, but I invite you to check the paper. But the second aspect of hardware-software co-design here is data and computation flow coordination, such that this partitioning actually does not lead to additional data movement overhead itself. And second, we reduce the number of writes to the NAND flash chip so we don't hurt the lifetime. The third aspect is a storage-aware algorithm. So we sometimes need to fundamentally rethink what efficient algorithm would look like when we are looking at this drastically different, let's say, hardware scenario underlying here. And the fourth aspect is lightweight in storage accelerators. How can we have these very lightweight hardware units so that they don't rely on neither large DRAM or SRAM buffers? And finally, the fifth aspect is data mapping scheme and flash translation layer that are tuned and specialized to unique characteristics of this metagenomic analysis pipeline. So there are a lot of results in the paper, but I want to particularly focus on one plot here to show what these storage-centric systems could potentially could enable in the future for these class of data-intensive applications, and that is about cost efficiency. So consider 2 systems. One is a cost-optimized system with a cost-optimized low-bandwidth SSD with 64 GB of DRAM. And the other case is a performance-optimized system, much costlier, with a performance-optimized SSD with higher bandwidth and 1 TB of DRAM. And now let's look at this plot. So we have 2 baselines, the performance-optimized and accuracy-optimized metagenomic analysis tools. And we run these tools on both of these systems, on the cost-optimized and performance-optimized system. And I also want to emphasize the fact that MIGIS reaches the same accuracy as the accuracy-optimized baseline because it doesn't make compromises to shrink the database size. So anyway, here we observe that on comparing on the same system, let's say apples to apples, we observe large benefits from MIGIS, but also we see that MIGIS outperforms the baselines even when running on a much less costly system. So we hope that such type of designs would enable making these data-intensive applications more cost-effective in the future and facilitate their wider adoption. And again, there's a lot more in the paper, so I invite you to check, and also we can discuss throughout the conference as well. So I want to also very briefly mention, without going through details, these more emerging areas that we've been looking in as a group. So the first one is about large-scale genome graphs. So as opposed to encoding these larger scale sequences as basically linearly as linear sequences, these graphs encode these sequences as walks in the graph. And they are more powerful and efficient representation of genomic data because they have greater expressive power because of their topology and the metadata. And also they have more compact representations of massive population scale databases. And these population scale databases have can provide phenomenal roles, for example, preventing, let's say, local epidemics to turn into global pandemics. So it's a lot of benefits to having this population scale genomic analysis. So yeah, we in our work design Grains, which is the first in storage processing system for large scale genome graphs. And what we do is that we first make this complex genome graph analysis more storage friendly via specialized execution flow and scheduling. And also what I want to emphasize is that these graphs have different topologies and therefore the operations would have different access patterns compared to, let's say, more conventional graph structures. So we specialize it based on these genome graphs, execution flow and scheduling. And second, we further improve performance, energy efficiency, and cost effectiveness by in storage and in flash processing techniques. And we show that it can provide significant speed ups and energy reduction at low cost compared to state-of-the-art approaches. This other one, more newer topic is the raw signal analysis. We've seen examples of it today, and also Konstantina will be talking a lot more about it, so I will just skip it. She will talk about the benefits and also the new type of storage-centric design that we came up with for this application. Yeah, so that's the paper that we recently published, and she's going to talk more about. So before my conclusion, I want to also briefly mention this other work, SAGE. So I want to, like this figure, I think that in every related venue or conference, we will see this figure several times. So yeah, I had to do it too. So anyway, after the development of high throughput and low cost sequencing, we see this very fast growth rate in genomic data. And as we have seen, there's been a lot of great efforts to accelerate genome sequence analysis, but also at the same time to store this genomic sequence data in highly compressed formats, because otherwise it will be intractable to deal with the fast rate that this data is growing. So the problem that we looked at in this work is data preparation bottleneck, where genomic sequence data is stored in compressed form and needs to be decompressed and formatted first before an accelerator can operate on it. And as we also saw in Sangbu's talk, there are different, like we need whole new approaches to compress this genomic data because general purpose compression would not work because they cannot capture the long range similarities that we have in DNA data. So anyway, let me show you with a simple pipeline what this data preparation bottleneck actually does. So consider baseline, we are preparing the data, decompressing, formatting it to desired format to feed it to the whatever system that is doing the analysis for different batches of data. And consider the second case that we accelerate the analysis, great. But also this third idealized case that we also ensure that the preparation is faster, or at least like as fast as the analysis, so it's not bottlenecking the whole thing. So comparing the first and third case shows us that there's a lot of potential that can be provided by all these efforts that we've done in the community to accelerate this genome analysis. But a large part of the benefit can be amortized because of this data preparation bottleneck. And the goal of SAGE basically has been, the goal of us in designing SAGE has been to mitigate this bottleneck. And SAGE is an algorithm architecture co-design for highly compressed storage and high performance access of large scale genomic sequence data. And the approach we take is that we exploit properties of genomic data that are inherent in the data to synergistically co-design algorithm and hardware such that we achieve high compression ratios comparable to the state-of-the-art genomic specific compressors and have fast decompression using only lightweight hardware and efficient streaming accesses. So what this second point enables is that it can integrate, it enables SAGE to integrate with genome analysis systems, even in resource constraint environments without requiring expensive resources, such as high bandwidth in memory or high capacity. And examples with portable systems or near data processing systems in memory or in storage, as we saw in previous parts of my talk. And we show that actually SAGE improves average end-to-end performance and energy efficiency of genome sequence analysis accelerators significantly. So it enables us to leverage these accelerators much better and unleash more of the benefits that they can provide. And there's a lot more, again, in the paper. So I, again, invite you to check it, or we can chat together also. So in conclusion, storage-centered systems for genomics can provide large benefits, such as improving performance, energy efficiency, cost effectiveness, and also, while I didn't talk about it in detail, didn't dive about it in detail in this talk, it can also help with robustness and like security and privacy. And we hope that all these efforts would help making accurate metagenomic analysis more accessible for its wider adoption in the future. And yeah, there are like also more things going on we're doing in different aspects, like algorithm size or hardware software co-design, or more on the storage, purely storage, or other modes of near data processing that we've been focusing on. And I invite you to check my website if you're interested. And yeah, thanks for listening and take questions.
Thank you, Nika. So do we have any questions from the audience?
Hi, thank you for the great talk. I'm a bit interested in the compression algorithms that are used for the genomics. So like for compression, I think there should be some kind of patterns inside the genomics that can be exploited. Well,
some kind of what that can be exploited?
Patterns?
Yeah, okay, yeah, great question. So what compressors do is that they find these patterns in some ranges, right, in some blocks. But then since the range of these similarities can be very long, as Sangbo also mentioned, if we go with whatever conventional technique, the dictionaries we would have or the lookup tables we would have would be huge. So instead, what we do is that since these partitions, these reads that I talked about in the read set or in a data set, are extracted from some reference genome or from some genome of organism, what we can do, and these genomic sequence specific compressors do, is that they try to map these reads to some reference, either given or they generated by overlapping these reads together. And by mapping these reads to that consensus sequence, I'm going to use the word consensus, you can encode the similarities and differences between them. But what happens is that you still need to use compressors on top of the information that you get from mapping. But if I want to give you the high-level idea of why they are better than general purpose compressors for genomic data, is that they leverage this property of mapping the reads to this reference genomes. Sure.
Other questions? Okay, maybe, okay, we'll talk later because we're behind schedule.
Yeah, sure.
So let's continue now.
So,
if they're in the downloads, it's me.
Okay, while you're switching, do I need the other thing also?
It's ideal.
We're running awfully late, as you can see, but which is good. There are a lot of people in the room. As I mentioned, we had actually a lot of interest in this workshop. We couldn't accommodate all of the talks. I think next time in HPCA, we'll probably have a full day. So if you're interested, definitely contact us. It's going to be in a nice place like Seoul, Sydney, on this end of the, let's say, world, but in the southern hemisphere, with probably better weather at that time in Sydney, right? I think so. Okay, anyway, the next talk is also from my group, Konstantina. She's a postdoc working on, again, architectures for bioinformatics. She's been with me for about 2 years, right? Maybe she's thinking right now.
A little bit less
a little bit less than
yeah.
that, but she did her PhD at the National Technical University of Athens, where she worked on accelerating genomics as well. And I was on her PhD committee, and I gave her a hard time at the PhD committee. But she figured out that was not hard enough, so she decided to work with me as a postdoc afterwards. So maybe she regrets that decision, but hopefully not. So she's still doing great work. She's going to talk about a work that we published at ICS this year, which is on, again, in-storage acceleration at different parts and using different types of processing in memory techniques of raw signal analysis that you have heard a little bit about earlier in your talk, right? Okay.
Great. Thanks a lot for the introduction, Onur. So now let's continue with diving more deep into the specific work done by Safari for in-storage processing of genome applications. So Mars is our newest work that leverages processing in memory techniques to accelerate and implement raw signal genome analysis within the storage subsystem. So we will first begin with some background. Part of it or most of it have been already discussed, so I'm going to try to maybe reduce some of the time. So as we've seen, studying genome helps us understand the genetic variation, understand the species and an evolution, and has led to some groundbreaking results in fields such as evolutionary biology, outbreak tracing, and precision personalized medicine. So typically, we've seen so far that the genome analysis always begins with two steps, which is the sequencing and the mapping. During the sequencing, we have a DNA sample that is input in a sequencing machine and generates small fragments of the DNA. This could be, these are usually initially raw signals or base called signals. Then we have the mapping, where we use these signals in small reads to align them in a reference genome and try to predict and find the most possible positions for these reads in the reference genome and reconstruct the genome of the initial sample. So typically after the sequencing, we usually have this base calling step, which is based on deep neural networks and translates the raw signals into bases. This is a very important step that secures some less noisy analysis and very high accuracy. However, it has the important disadvantage of being extremely costly and power hungry. So recently, there's been an alternative to this way of manipulating and working on reads, and this is the raw signal genome analysis that directly maps the signal to the reference genome without doing the base calling first. So this manages to do some efficient analysis, scales better, and also is portable. And on top of that, it can also give us some extra information, as raw signals manage to contain richer information than only bases. So we're going to focus on raw signal genome analysis that operates directly on the raw replica signals. And it allows us to explore the high throughput of the sequencing technologies and even do applications in real time. So raw signal genome analysis can be also divided into two major steps. One, we have the indexing that is happening offline, and then the mapping that is happening online. So for the indexing step, first we need to transform the reference genome that is usually stored in bases, in current databases. So then we transform it into raw signals, and we do some sketching mechanisms so that we extract small parts of the reference genome that are called events. Then we use these events to generate some hash values and create a hash table that will then speed things up when we look up the positions of the incoming raw signals to the reference genome. So then during the mapping, we can see that there are two main steps to do it. So first of all, we have the query sequence. It is a raw signal. And through the event detection step, we use some sketching mechanism to create some smaller parts of the initial raw signal that are called events. Then we have the seeding step. We apply some hash function on the events. We generate some hash values that are used to query the hash table to find potential positions matches to the reference genome. Once these potential matches are returned to us, which are called alternatively seed hits, we can move on to the chaining step. So in the chaining, we try to group these matches in some collinear positions so that we have some very close representative of the actual alignment. And this is heavily based on doing sorting and dynamic programming algorithms. So now that we've had a small introduction to raw signal genome analysis in terms of more algorithmic than in previous presentations, let's go on to the motivation of this work. So we've seen that the sequencing throughput of sequencers is currently growing rapidly and is expected to continue to increase with this rhythm. And raw signal genome analysis, despite being very efficient, it still struggles to meet the increasing requirements and also satisfy some real-time applications. Therefore, there is a need to accelerate raw signal genome analysis.
the way to do that would be first to identify the computational bottlenecks. So therefore, we have performed here a breakdown of the steps of raw signal genome analysis by using 4 different data sets from organisms that are scaled from the smallest one, which is D1, to the largest one, which is D5. And we can see in this breakdown that the seeding and chaining are one of the most important computational bottlenecks, and they are consistently dominating the execution time for all genomes. What we can also see is here that the event detection also takes up a significant amount of time. And the most interesting part comes when we consider this input-output overhead. We can see that it is larger for smaller genomes and smaller for larger genomes, but this motivates us to look more into it. So for that reason, to understand holistically our system, we're going to model how the IO data movement behaves when we're starting to accelerate the obvious computational bottlenecks. So we leverage some accelerators for the seeding and chaining parts, and we see that the IO overhead is actually increasing and becomes the most dominant part when the reduction of the end-to-end latency is basically increasing. So this indicates that in order to have an overall efficient system, we need to design a high-performance and energy-efficient system for signal genome analysis by addressing both the IO data movement as well as the computational bottlenecks. So this brings us to introduce Mars. So Mars is the first in-storage processing system for raw signal genome analysis. Our key idea is to create an in-storage processing system for RSGA that addresses the IO data movement bottleneck and also exploits the capabilities of SSD for parallelization to accelerate the computational intensive steps. So Mars is a co-design between targeted software modifications and some dedicated hardware components within the storage system. The software modifications aim to optimize the steps of raw signal genome analysis for efficient execution within the storage, while the dedicated hardware components are accelerators implemented using processing in memory within the SSD. And in this work, we actually leveraged 2 different paradigms for doing the processing in memory, which is processing using the SSD internal DRAM and also processing near the SSD internal DRAM. So let's first go through the software modifications before seeing our overall architecture. So regarding the software modifications, the goal behind them is to reduce both the computational workload of RSGA, but also reduce the storage requirements. So we have 2 different types of software modifications. First, we adopt some filtering techniques, such as frequency filters and also some vote-based filtering, with the goal to discard any candidates and seed heads that actually don't result in valid alignments. We also couple these filtering techniques with arithmetic conversion techniques. Instead of using the floating point arithmetic that is used in typical workflows, we explore and examine the benefits of fixed point representation with the goal to reduce the memory footprint as well as the computational cost. The challenge in adopting these optimizations is to preserve accuracy when applying these to raw signals for the first time. To achieve that and preserve the accuracy, we actually have to be very careful about which places in the pipeline we decide to place these techniques. And we have to do some also fine-tuning based on input dataset characteristics. We validate that we actually have a good accuracy by comparing our accuracy with a ground truth that is based on a typical base calling based pipeline that consists of Dorado base caller and Minimap 2 read mapping. And we also compare against the RoHS 2 state-of-the-art raw signal genome analysis solution. In this case, we're going to also examine both 2 variants of our workflow. One of them only adopts the filtering techniques, and the second one also adds on top of that the arithmetic conversion. And we can see indeed that our variants overall improve recall and F1 score over RoHS 2, which shows that our filtering techniques are very effective in eliminating any redundant reads and focus more on reads that provide useful information and target the informative regions.
But also, if we also see in isolation only the two variants of our Mars, we can see that the fixed point arithmetic only leads to minimal accuracy loss. And this is thanks to our very strategic placement within the workflow. So now that we have established that we have provided with an accurate solution, let's go to see a high-level overview of our architecture. So Mars is implemented within the storage system, and the SSD operates in two modes. First, we have the conventional mode. In this case, the SSD performs the standard operations. And then we have the accelerator mode. In this mode, we execute the full RSGA pipeline without needing any host intervention. So let's go and see the components one by one, starting first with the ones that are instantiated within the SSD controller. So first, we have the Mars control unit. This is implemented as a finite state machine that orchestrates the pipeline execution and the data and the control flow. Next, we move on to two units. This is the sorter and the merger unit. These are also implemented within the SSD controller. The sorter unit is responsible for performing parallel execution of the sorting that is required. And the merger unit is responsible for combining already sorted subsequences into longer ones. These are implemented with logic within the SSD controller, employing the processing near DRAM paradigm. And we have one pair per each flash controller inside their system. Next, we move on to the components that we use within the SSD internal DRAM. First of all, the arithmetic unit. This is dedicated to performing arithmetic and logical operations. So all steps of RSGA that do computation are executed on this place. That is implemented using processing near DRAM. It is designed based on a fulcrum architecture that leverages the DRAM subarray proximity to do low latency parallel arithmetic operations. Due to the size of this unit, we have to use two subarrays for one instance of this one. Next, we go on to the querying unit. The querying unit is specialized into performing efficient in-memory hash table lookups for the seeding part. We implement this by processing using DRAM, and it is based on the Pluto architecture. In this case, this unit is smaller, so we managed to fit one per subarray. So now that we've seen all individual components, we can see how we implement the entire Mars pipeline. So first, we need to break down the steps of raw signal genome analysis of Mars into some fine-grained tasks that can be straightforwardly mapped to our operations of arithmetic, querying, and sorting, and computational units. So once we have these fine-grained tasks, we then map them to our computational kernels. So for example, if we have some multiplication in any step of the raw signal genome analysis, this is going to be mapped to arithmetic unit necessarily. Next, we use this new pipeline of tasks, and we use it to encode a finite state machine that defines a fixed execution sequence. But each step is dynamically triggered when the data is ready and not necessarily executed if not necessary. For example, the sorting is always done, but maybe the merging is not necessary to happen. So next, in order to have a better understanding of the flow, we have here some figures to show exactly how the data flow from different parts of the SSD. So we start with our input data. These are initially in flash memory, and we transfer them to the SSD internal DRAM to perform first event detection in the arithmetic unit. Next, we're going to have to do the seeding part. In the seeding, we start by generating the hash values and doing some filtering. These are also done with arithmetic operations, so this is also done in the arithmetic unit. Once we have the seeds, we have to, not the seeds, sorry. Once we have the events, we have to look them up in the hash table. So we're going to utilize for this the querying unit, which is again inside the internal DRAM. Now that we have the seeds available, we're going to have to go on and create batches of them to send them to the SSD controller to do the sorting. So we send some unsorted sequences in batches. The sorting happens in the SSD controller from the sorter and merger unit. And once we have the sorted sequences, we send them back to the internal DRAM to perform the final step of chaining that is based on dynamic programming. So this was the overall flow. You can see more details about the mechanism and the system integration in the paper. And now we're going to move on to seeing some evaluation results. So in order to evaluate Mars, we're going to compare with 4 systems. First, we have a typical base calling based system that is running base calling on a GPU with Dorado and the alignment with the CPU. Next, we move on to our second baseline, which is a hardware accelerated, an NVM-based hardware accelerated pipeline that does, again, base calling and read mapping. This is GenPip. Then we have a state-of-the-art software CPU-based RSGA pipeline, which is RoHS 2. Only the software version of Mars, and finally, the full system Mars implementation within the storage subsystem. Let's see now about our system. In order to evaluate all the CPU-based baselines, we use a server that has 2 AMD CPUs with 64 physical cores and 1 terabyte DDR4 DRAM. The part that are executed on GPU are run actually on NVIDIA RTX A6000 GPU. Our SSD configuration is 8 channels with each one having 8 flash chips, PCIe 4 interface, and 4 GB internal DRAM. And lastly, for all the accelerators that we have created, we have used Synopsys. And for emulating all storage and DRAM operations, we use MQSIM and Cacti 7. So here we can see the results. We can see indeed that Mars manages to outperform all the other baselines across all the data sets. It is very important here to notice that it manages to outperform GenPip, which is adopting processing in memory, but outside the storage, which clearly indicates that we managed to outperform this because we fundamentally solve the input-output data movement overhead. Similarly, it's also important to notice that even our only software implementation manages to outperform the software state-of-the-art, which shows that the software optimizations that we have adapted are very effective in reducing the computational load. Similarly, good results we also acquired through energy, and we can see that the Mars manages to reduce energy consumption over all the other baselines. And this improvement comes both from reducing the execution time, but also because we have managed to diminish the I/O data movement overhead. So then we reach the conclusion of this work. So to summarize, we have presented Mars, which is the first storage processing system for end-to-end raw signal genome analysis that is enabled through software improvements and deploying PIN inside the storage system. We have managed to improve performance over both software-based and hardware-accelerated base calling-based and RSGA-based pipelines. We have also managed to reduce energy consumption while at the same time preserving very high accuracy. So thank you very much for listening to this talk, and I'm happy to take questions.
You attracted a very large crowd.
I saw they were.
Questions? So maybe meanwhile I ask also one question myself. So you mentioned about the benefits of analyzing the sequencing data directly. So what do you envision would be the benefits if we have, let's say, accurate and very fast, much faster base callers developed later?
So I think that it is important to still work, of course, in the base domain. But even if this becomes extremely fast, raw signals could have an advantage because they manage to encapsulate richer information than only the information about which is the exact base. So I think it can basically enable a different type of analysis, and they ideally will work in some hybrid mode.
Right, makes sense. Great, thank you so much.
Thank you, Nika.
So maybe
we can
if there
move
are
on.
no burning questions, maybe we can move on with the
Yeah, I think so too.
speaker. Noelia? Are you good at her files? Yes. Can you let me know how to pronounce your next name? Or this is called, or it is called us.
So Nika, I have one slight issue here. Now it's a PDF.
Yeah.
Yes, I will say again, sorry. It's not a problem.
Oh, it's actually running out of time. It's fine.
Yeah,
Yeah,
I'm sorry. Okay, we can see it here, but this is the best I can do, right? Is it, it's
I
a,
think that there is a button in this is like an right?
okay, yes.
And then,
Sorry about that.
mm,
Is it?
there is no view, and then view as a presentation names. Or F5, maybe? No,
This is not, for me, it's a,
F8, I don't remember. And this one, right here, this button. No. Full screen mode. Okay, this one.
okay, cool, great.
Okay.
Okay, but you have to do it probably manually, I think.
Yes, so now it's kind of like run over the official time of the workshop. But anyway, your talk will be live streamed and also available
Yeah,
on
don't
YouTube, so
worry.
another people.
That's okay.
Great, okay then. Floor is yours.
Okay. So Noelia Lieteswen is a PhD student in computer architecture at UPC. She received her bachelor's degree in computer engineering from University of Zaragoza in 2022 and her master's degree in advanced telecommunication from the UPC. She's currently working as a research engineer for the Encore Hash Hierarchies and Interconnect Group at the Barcelona Supercomputing Center. Her research interests are in computer architecture focused on memory management, hardware acceleration, and learning indexes. Thanks, Maria.
Okay, thank you. So let's start. As said, my name is Noelia, and I'm going to present our work, which is a tightly coupled hardware accelerator for fast pattern exact matching in genome analysis. This is a collaboration between Barcelona Supercomputing Center, the University of Zaragoza, and the University of California in Santa Barbara. Okay, so brief introduction. As you already know, the genome is the piece that contains the genetic information of organisms. Analysis genome is key because it allows us to drive advancements in topics such as biomedicine or even agriculture. Genome analysis tools need to perform pattern exact matching operations, or PMOs, in huge genomic databases, and this is a very challenging process even for high performance systems because it requires a lot of time and presents a very, very low throughput. To perform fast PMOs, many tools rely on the space-efficient FM index structure, which basically allow us to perform PMOs in which we will search one base pair per step, having a complexity of ON to search a pattern of n base pairs. So here on your right, you can see a figure in which more or less I want to explain the algorithm. So first of all, in the initialization step, we will initialize 2 pointers pointing to the first and to the last position of the genome database, and then we will start iterating, doing basically random accesses to the genome database until we find the entire pattern that we are looking for. So as you can see, this is a very disadvantaged algorithm because it presents a very random memory access pattern that causes poor spatial locality, and basically we have an inefficient use of current memory hierarchies and bandwidth. So a recent proposal that is called LISA proposed to accelerate these FM index PMOs through a learning index model, which is basically a machine learning model which is trained with the application data pattern, which in our case would be the genome database. They report a 4x speed with respect to FM index implementations. Leveraging this machine learning model, what it does is to basically reduce the number of steps that are needed to perform a PMO, and which is more important, to reduce the random memory accesses, which are the most costly ones. So how it works? So basically, with this approach, we can now perform searches of k base pair per step instead of 1 base pair per step, downgrading the complexity from ON to ON divided k. So the algorithm performs in 4 stages. The first one is the key generator stage, in which we will generate a key from the pattern that we are looking for and the initial position of the search. Then this key is used as the input of the machine learning model that will generate a prediction of where is located this pattern. Then in the last stage, which is the binary search, we will correct the error of the machine learning model, making a search within the limits of the predicted precision plus minus
the error of the model until we find the correct location. That is possible because the genome database is sorted. So, although this is a very promising proposal, it still presents important performance limitations. Here we have, on the right, we have made an evaluation of different metrics such as IPC, last level catch and PKI, average number of cycles to perform a load, and a percentage of misspeculated instructions. As you can see, even for the smallest database, which is COVID-19, that fits in L1 catch, the IPC that is reported by the algorithm is very, very low because it is just 1 instruction per cycle in a machine that we can commit up to 8 instructions. Also, we can see huge ratios of last level catch in PKI and huge number of cycles to perform a load instruction. Additionally, we can see also a very huge percentage of misspeculated instructions. This is because, as you know, the binary search is a very presents a branch-heavy nature that will cause that the branch predictor basically misspeculates a lot, generating a lot of instructions. So then we have 3 disadvantages. We have limited instruction level parallelism, poor memory locality, and a high instruction speculation. Recent proposals such as XMAN Bless, which was later presented, and to address this limitation by presented loosely coupled hardware accelerators. But we find that there are some limitations in terms of performance, efficiency and scalability, and flexibility and integration. In terms of performance, those accelerators don't take into account that they have to perform data transfers that are very costly because they use DMA or IO transfer as they are loosely coupled from the CPU. And they also, as they are non-coherent accelerators, they need to perform synchronization mechanisms, and this will require a lot of cycles of overhead because they use techniques such as catch losses, but because these techniques are very costly. Regarding efficiency and scalability, they tend to replicate components that are already in a CPU because they are not tightly coupled to it, and this will incur in extra area and power overheads. For example, Bless replicates memory controllers or the physical layers. Finally, regarding flexibility and integration, they do not support different key values and pattern lengths, and uses ad hoc interfaces that demand deep architectural knowledge. So in this work, we propose PITS, which is an efficient and flexible hardware accelerator based on learning indexes for fast pattern matching operations on large genome databases. Our contributions are that first, we propose a user-friendly interface for PITS that will allow seamless integration with CPU code. Then we also present an efficient PITS hardware design that is tightly coupled with the CPU, exploits PMO parallelism, leverages CPU resources, and scale with multi-core systems. We also evaluate PITS using Gen5 and demonstrate that we perform state-of-the-art solutions up to 47x. And finally, we demonstrate that PITS design is area efficient, achieving up to 45x more efficiency than the state-of-the-art. Okay, then let's continue with PITS architecture. As you know, modern chip architectures are based basically on a multi-die design in which each tile is interconnected using a network chip. Then in each tile, we can find a CPU and a catch hierarchy of 3 levels. In our case, we will place PITS tightly coupled to the CPU, and the communication between the accelerator and the CPU will made through 2 custom instructions that we call PMQ and PMR. PMQ basically sends the pattern that we want to search, and PMR is the instruction that is used to retrieve the result from the accelerator. So then let's go with the microarchitecture. PITS basically exploits the fine-grained level of the PMOs through a concurrent stage pipeline microarchitecture that hides the large memory access latencies that are caused by this random memory access that inherently has the application. So PITS design is divided into 7 pipeline stages that are very simple, starting from the first one, which is the query handler stage. Is the stage basically that receives the PMOs through the PMQ instruction that is executed by the CPU in the commit stage. Then in the second stage, the load query will retrieve a keymer or a chunk of the pattern that we are searching of key-based pairs from the memory system. Then in the next stage, the key generator will generate the key that is needed to evaluate the machine learning model. And then in the 2 second stages, we will evaluate the 2 layers of the machine learning model. Then in the binary search stage, we perform basically the binary search and in the predicted range, which basically takes the predicted position from the previous stage. And we also will check if all the chunks of the pattern have been searched or not. If it is not the case, then we'll repeat the pipeline starting from the load query stage. But if it is the case, then we will go through the last stage and keep the result. Additionally, in this work, we'll present PITC, which includes a read-only catch to exploit the locality that we found in the last step of the binary search. So then in the final stage, the commit stage keeps the PMO result until a PMR instruction will retrieve it. Okay, so then continuing with the experimental evaluation, first of all, the methodology we have used for the cycle level simulation, Gen5, which is the state-of-the-art computer architecture simulator, evaluating 16 numbers V1 like after 4 records. For the RTL design and system synthesis environment, we have designed the accelerator in system Verilog, synthesizing in 7 nanometers and targeting the same frequency as the CPU, which is 2.4 gigahertz. And then as datasets, we have used as genome database the human genome, and we evaluate different PMOs varying the pattern length and also the key value. Okay, so then going through the results, overall performance. Basically here in this graph, we compare PITC and PITC, which are our proposals, again the CPU software baseline, and also with respect to the state-of-the-art hardware accelerators, EXMA and BLES. We compare it in terms of throughput, which is measured in megabits per second. As you can see, PITC and PITC outperform LISA, achieving up to 38 higher throughput, and also we improve the throughput of up to 47x with respect to EXMA and 1.77x with respect to BLES. Then how it comes this performance? So basically here we have median analysis with respect to the CPU software baseline, and here we demonstrate that we reduce the number of executed instructions and last level catch accesses, or more important, the last level catch misses. With respect to executed instructions, we can reduce it up to 42x. That is because now we are, instead of evaluating the PMOs in a CPU, then we are evaluating PMOs in a specific hardware. Regarding last level catch accesses, we reduce up to 2.31x. This is basically as now the binary search is executed in a specific hardware, then we don't mis-speculate. So then basically all these accesses that were caused by mis-speculation disappear by implemented it in hardware. So then that is why we reduce the number of last level catch misses, or more important, main memory accesses, which are the most costly ones, up to 2.74x, and those also improving memory bandwidth efficiency. So finally, the lab results. This is a physical design analysis. As I previously commented, it was synthesizing 7 nanometers, and the total area of pitch and PITC is 0.08 and 0.09 millimeters square per core tile, which represents a 3.5% of the total area of 16 Army/V1. We demonstrate that pitch and PITC are the most efficient solutions, achieving up to 34x more throughput per area than LISA, 45x than EXMA, and 2.26x more than BLES. As conclusions of this work, as I said, genome analysis is very important to drug advancement in biomedicine or agriculture or a lot of more topics. We present PITC, which is a hardware accelerator based on learning indexes or machine learning that accelerates the genome analysis through the acceleration of these PMOs. PITC basically maximizes PMO parallelism through its fine-grain level concurrent stage pipeline that has basically the large memory access latency. Also, PITC is tightly coupled with the CPU, so then we reduce data transfer overheads, reduce CPU resources efficiently, and scaling multi-core systems. Additionally, we present a flexible design that supports different genome databases, pattern lengths, and key values with a user-friendly interface for simple integration in end-to-end applications. And finally, we demonstrate that each performs state-of-the-art proposals with up to 47x more throughput and up to 45x more efficiency. So thank you all for your attention. And if you have some questions.
Thank you very much for your talk. Do we have questions from the audience? Maybe we can fit a question. No? Then maybe I can ask the Q1. I'm wondering, sorry, was there a question? I missed it. No. Okay. So that I can ask my own. So you're focusing here on exact matching.
Yeah.
And I'm wondering if you see any prospects in utilizing some of your insights from this work for approximate matching, or if you could see this work being used for some sort of filtering or hybrid cooperation with approximate matching.
Yeah, I think that one of the uses, for example, for super maximal exact matching, for example, would be to use the accelerator to do the part of the exact matching and then use software code along with the accelerator to use the accelerator for other proposals. So then you can combine software and the accelerator to amplify the field of the use case.
Do you have plans to implement this yourself?
Well, we will see in the future, but now this is my research now, and it is not published, so we are trying to
nice.
publish it, and then let's see.
Great. Thank you very much.
Maybe in the next iteration of the workshop we can present it.
Yes.
Yeah. Thank you.
So we have one last talk, which is online from Lucas from CERN.
Good afternoon, everyone. Yes, can you hear me as well?
Yes. So we have
Awesome.
I'm a little bit late, but yeah, this was the last talk. And Lucas is in Switzerland right now, and that's in the morning for him. Yeah, okay, so I will
I think we can see
share
your
his bio.
I think you can see, but we see an empty screen for now.
Maybe you can share your slides, Lucas. We can see some trees. Great. Yeah. So
Okay,
Lucas
perfect.
Lucas is an experienced software engineer and researcher with a passion for developing efficient and large-scale systems. As part of the root team at CERN, he's accelerating physics data analysis on the GPU. Prior, Lucas was a lead developer of the agent-based simulation platform Biodynamo and its major improvement Terra Agent. Lucas holds a doctoral degree in computer science from ETH Zurich, where he was part of Onur Mutlu's Sapari research group. His research interests include high-performance parallel distributed and heterogeneous computing, and his application in research, biology, medicine, and beyond. So, Lucas, you can go ahead.
Thanks very much for the introduction, Nika. Yeah, good afternoon, everyone. I'm very happy for the opportunity to present the current state and the future directions in scalable agent-based simulation with Terra Agent, which is a work that I did mostly during my PhD. So to explain what agent-based modeling is, I want to start with an example that models swarm behavior, as can be seen in this video. So in this example, the agent is a bird which has two attributes, a position and a velocity. So in the simplified 2D model that you can see on the right, birds are here represented as a dot, and they're initially randomly distributed. By default, these birds move straight ahead, but Craig Reynolds in his 1987 article distilled 3 bird behaviors. So let's activate them one after the other to see what happens in the simulation. So first, the agents are avoiding the collisions with nearby flockmates. Then second, birds align to the velocity vector of the neighbors. And third, birds try to stay close to each other. So we can observe here that these 3 simple rules give rise to the natural swarm dynamics, although we didn't program that in directly. And this phenomenon is called emergent behavior and describes that in agent-based modeling, the whole is greater than the sum of its parts. The second agent-based characteristic is local interaction, as we can see from these 3 behaviors. Agents only interact with their immediate surrounding. So agent-based modeling is a very versatile approach and is used in many different domains, as you can see on this slide. modelers first have to define what the abstract term agent represents. So we've seen first before like a bird, but it could also be a cell, a person, cars, or traders, depending on the use case. Afterwards, the researcher has to define the behaviors which define the interactions between the agents. So together with our domain experts, we identified two key problems. So first, many existing agent-based simulators have an inflexible software design, and second, they exhibit low performance. So based from this observation, we derived the following thesis statement, which says that an agent-based simulation platform that is designed from the ground up to be high performance, scalable, and modular can first significantly reduce the simulation runtime and thereby enable larger and more complex simulations, faster iterative development, and more extensive parameter exploration. And second, significantly improve the adoption and thereby enable advances in many different domains. So our approach to prove this thesis statement is divided into three main contributions. So first, BioDynamo, which is a modular and feature-rich simulation platform. Second, the high-performance parallel simulation engine. And third, a distributed simulation engine called TerraAgent for extreme scale simulation, hardware flexibility, and improved interoperability. So let's begin with the design and implementation of the simulation platform. So this first contribution addresses the inflexible software design problem, which is often caused by the specialization to a specific use case. So this figure here shows the different abstraction layers of BioDynamo. So on top of the hardware, operating system, and third-party libraries, BioDynamo adds low-level features, which are mostly hidden from the user to hide its complexities. In the middle, we provide high-level features, which represent agent-based functionality, which is required across many domains. And at the top, we provide model building blocks for functionality in specific domains, for example, in neuroscience. So these abstractions and interfaces that we defined ensure that additional functionality can be added easily. So we implement the following simulations to demonstrate BioDynamo's capabilities. The first is a simple cell proliferation simulation. Then we have cell clustering, and lastly, a use case in neuroscience. There are also use cases in epidemiology to simulate the spread of an infectious disease, and in oncology, which is a simple example of tumor growth. So of course, we validated these models, and here I want to show the neuron model as an example, which we validate both qualitatively and quantitatively against real neurons. And what we can observe on this slide here is that they are in good agreement with each other. So this visualization here shows the same neuron growth simulation that we've seen just before in the validation, but on a much larger scale with around 10 million agents. So much more details about the platform, the features, and the simulations can be found in our bioinformatics paper. I want to continue now with our second contribution, which is the design and implementation of the shared memory simulation engine. And as you can imagine, this contribution addresses the low performance problem that we have identified. So low performance has the following implications. It first limits the model size and complexity that can be simulated. It increases the development time because agent-based models are developed in an iterative way during which a model is more and more refined. And lastly, it limits the capability to optimize parameters, or it increases hardware costs, depending on the way you want to look at it. On this slide, you can see the microarchitecture analysis for our 5 different simulations. And this analysis shows inefficiencies in the processor's pipeline. Here we make the following key observation that these agent-based models are predominantly memory bound, and this means that data transfers between the CPU and the main memory are a major bottleneck. To address this issue, we make the following performance improvements. So first, we improve the memory layout to reduce data transfers with number-aware iteration, agent sorting, and an optimized memory allocator. Second, we maximize parallelization by optimizing the radial neighbor search algorithm and parallelizing the additions and removals of agents. And third, we avoid unnecessary work by avoiding pairwise force calculations for static regions, which are areas where agents do not move. So we evaluate these improvements with the 5 simulations from our first contribution. And this table here shows that they cover a broad spectrum of performance relevant characteristics. So let's begin the evaluation with a scaling analysis. So on the left, you see the left figure plots the speedup with respect to a single threaded execution, while the right one plots the absolute runtime in milliseconds. So now let's enable our optimizations step by step to see the impact on speedup and runtime. And what we can observe here is that Biodynamo scales well across a large number of CPU cores. So we also compare Biodynamo with Biocelian, which is an agent-based framework for tissue models, which is also optimized for performance. So we implement their cell sorting simulation presented in the Biocelian paper and use identical model parameters. And our performance analysis shows that Biodynamo is up to 9 times more efficient than Biocelian. We also investigate the runtime and the memory consumption with varying simulation sizes, starting from 1,000 agents until up to 1 billion agents. And here we can see that the runtime and memory increases linearly once the simulation reaches a size that fully utilizes each processor's core. Again, more details about the optimizations and the evaluations can be found in our PPOP paper. This brings me already to the third contribution, which is the design and implementation of a distributed simulation engine called TerraAgent. So with this work, we address key issues of the shared memory engine from contribution number 2, which is first, that the model size and the complexity is still limited by the compute capabilities of one server. Second, there is still limited hardware flexibilities. So if a user wanted to execute a large simulation, they had to use a powerful server for that. And third, there is limited interoperability with third-party libraries that are parallelized with MPI only. So to address these issues, we develop a distributed simulation engine. And this engine partitions the space into multiple volumes, as you can see on this figure here, which is called domain decomposition. And these subvolumes are then assigned to different servers. So at the intersection that you can see on the right in red, these servers have to exchange agent information in order to determine the update for the next time step. And we make the observation that agent serialization and data transfers are a significant performance bottleneck here. Therefore, we address these issues with 2 improvements. First, we develop a tailored serialization mechanism that avoids unnecessary overheads. And second, we reduce data transfers by using delta encoding and compression. So delta encoding exploits the iterative nature of agent-based simulation, as you can see in these 3 consecutive iterations that all look very much alike. So we evaluate TerraAgent on the Dutch national supercomputer and execute an extreme scale simulation with 500 billion agents. And we do that on 84,000 CPU cores. Much more details again about these optimizations and evaluations can be found in this paper here. So this already concludes the 3 main contributions. Next, I want to very briefly show 4 examples of the significant external impact and validation that Biodynamo had by other researchers. So this work shows that Biodynamo is capable of simulating systems whose complexity exceeds the ones that we've seen in the presentation so far. So researchers use Biodynamo, for example, to simulate vascular tumor growth and the response to drug treatments. Nika and his colleagues built a mechanistic model that could be used to estimate the probability of developing lung fibrosis after irradiation therapy, which was recognized as a top 10 breakthrough in 2024 by Physics World. Roman Bauer and his PhD student Onur modeled the development of the cerebral cortex and how the different layers form during development. And lastly, I want to show ongoing work about the CAR T-cell cancer therapy, which includes, so in this therapy, like blood is taken from the patients, the T-cells, as you can see on these infographics, are extracted from the blood with the help of a virus, like a gene is inserted to express like certain genes on the surface. These modified T cells are then replicated, infused back into the patient, where they bind and kill cancer cells. So this type of therapy is still very new, with several open research questions, where agent-based modeling can help to gain insights. One such model is from Luciana Melina Luc, which was published in Nature in 2024. And in his Google Sum of Code project, Salvador de la Torre Gonzalez re-implemented this model in Biodynamo and achieved a 2x speed up on a low-end machine without any profiling. So we are very confident that we can substantially improve the speed up in the future and use this re-implementation for further research of this therapy. So lastly, I want to briefly present 3 potential future research areas. So the first one is to take advantage of processing in memory systems. So as we all know, off-chip memory accesses are a fundamental bottleneck in today's computing systems. And so far, our optimizations that you've seen focus deliberately on accelerating Biodynamo and TerraAgent on today's hardware. So the problem here is that, of course, these optimizations, they do not address the fundamental issue, but so to say, only treat the symptoms of it. So therefore, our goal here would be to be a bit more forward-looking here and enable further performance improvements by utilizing PIM hardware. I see at least two options. First would be to examine the usage of real PIM hardware, for example, UpMem, or second, to contribute to the design space exploration of future PIM systems. So second research area would be to make TerraAgent more appealing to a broader audience. Currently, models are defined in C++ code, but the problem here is that C++ can be challenging for researchers that come more from a MATLAB or R-based background. So our goal here would be to enable, for example, Python-based model definitions, while at the same time, hopefully keeping the same performance characteristics of the current platform. So the goal here would be visualized on the figure on the right. The challenge here is user-defined classes that are written then in this higher level language here, for example, in Python, and the performance-related overheads, for example, of frequent crossings between the language barrier and also then the slow execution speed of example Python. So the third research area could be to extend the GPU support of TerraAgent. So TerraAgent currently is limited. The offloading capabilities are limited to mechanical forces, due to usability considerations. And the problem here is that there is a large potential for acceleration which is currently still untapped. The goal here would be to increase the amount of code that can be offloaded to GPUs. And a good first candidate would be then to offload substance diffusion, which is an important part of tissue models, and which is executed multiple times per iteration before data needs to be transferred. And the second one would be, which is again linked to the previous slide, the ability to execute user-defined behaviors or agents on the GPU, and then using a compiler-based approach to relieve users from the burden to write low-level GPU code. So to summarize this brief talk, the key takeaways here are that TerraAgent is the first agent-based platform that scales to 500 billion agents, which is an 84 times improvement. And this is on top of the already significant speed up of Biodynamo, which is up to 1,000 times faster than the state of the art. And lastly, I think there are many exciting future research directions, of which I mentioned 3 today. And yeah, we're very happy that this work received the Best Artifact Award at the PPOP conference, and very recently also the Impact Award from the Society of Research Software Engineering. And again, more details about all of this can be found in my dissertation. And lastly, I want to thank many individuals and organizations. Without this work would not have been possible. So thanks very much. And then this brings me to the end of my presentation. Thank you very much for staying with me, and looking forward to answering your questions. Thanks very much.
Thank you very much, Lucas. Does he hear us? Can you hear us?
Yes. Yeah, I can. I think there's a bit of a lag, but I can
Did
hear
you
you.
hear the clapping? We were very happy we clapped over.
Thanks.
Okay.
Thanks very much.
So any questions from the audience? Any questions? Great. So Nika has a question.
So Lucas, you mentioned very interesting examples at the end regarding real-world adoption of this in very critical medical scenarios. Are there some takeaways that you had from this close collaboration with people working in the medical field? Like your perspective as a more computer science person, how was it? Basically, how did you need to change the mechanisms, or what was the lessons in general learned from this close interdisciplinary collaboration?
Thanks. Yeah, like this is something that I enjoy very much, and I think like in our setting, this was really essential in order to in the end achieve the results. So like this project like brings together like a computer scientist. So like I was mostly working on the platform aspect, and then like domain scientists from various fields. So the example that I've shown like are mostly from biology or medicine, but we've also had like from other fields. And these were really essential because like they brought like these domain experts brought like their problems that they're working on, and described their problems, and had the modeling expertise to translate then different systems into the agent-based model. And through these discussions, we were driving steering the platform development, and then also like helping these domain scientists achieve their modeling goals. So yeah, for this kind of project, I think this was really, really essential, and benefited definitely the results.
Thank you so much. So yeah, it's time to conclude. We're running kind of late. I don't know, but the owner has some remarks to make.
Okay. Thanks, Lucas, for this very nice talk. It's good to see you online. Yeah, I must mention that Lucas did his PhD with me and CERN, and he did a wonderful job with Biodynamo. If people are interested in using it, it's all online, maintained. A lot of people in different communities have used the Biodynamo infrastructure. And there's no hardware acceleration in it yet, right, Lucas?
That's true, yeah.
Software, distributed software. Yeah. So if you're interested in building on it, there's a lot of opportunity, in my opinion, in this domain to do hardware acceleration as well. So if you do hardware acceleration, I think this could be even more powerful. Okay, so I think we're at the end. We have exhausted the time and come over. I think people are actually opening the door, trying to figure out whether we're done or not. They're going to kick us out sometime soon. But hopefully this was an interesting workshop. Hopefully people are excited. I know people have stayed for long. That's great. And as I mentioned, there's a lot of interest in this area, and this is a very broad area. So hopefully we will continue working on this. And if you're interested in contributing, being part of the workshop organization, we're very happy to involve dedicated people. And I know some of you are maybe interested. As I said, we'll have the next incarnation at HPCA. It's going to be a full day. And hopefully we'll have an Arch4Health dinner at HPCA. Today, unfortunately, we can go out for a more informal dinner with people who are interested. But the difficulty is, as my organizers pointed out, computer architecture community is not very good at scheduling their rebuttal and revision timeframes. The rebuttal and revision timeframe for HPCA is actually right now happening. When is the deadline? On Tuesday. So they have conveniently overlap the entire rebuttal and revision timeframe with another major conference, which should really not be happening, in my opinion. Maybe I'll have more of these musings in my keynote talk on Tuesday. And hopefully this will start a conversation on how we can do things better going into the future. But hopefully at HPCA we'll have a dinner. And at HPCA we'll also have the memory-centric computing workshop, which is going to be organized by Ismail and Nisa, who are sitting in the back, which is going to be synergistic with this workshop. Okay, if you have any feedback, please let us know to improve. And I will definitely thank people who have done most of the work, Nika and Konstantina over here. And I'll thank everyone else for attending and contributing to the workshop. Thank you. See you around. I have one more point. Oh, can we do better? I didn't think about this, but I think it's important.
Ends at 9 p.m. and the deadline exactly is at 9 p.m.
Yeah. Okay, that's okay.
Okay.